There are monsters lurking in the darkness of space, invisible, silent, impossibly powerful. They don't just destroy matter, they destroy time itself. They don't just bend light, they trap it forever. They don't just warp space, they tear holes in the very fabric of reality. Black holes are the universe's ultimate enigma, and tonight, I'm going to tell you 169 facts about them that will completely change how you see the cosmos. Some of these facts will fascinate you, some will terrify you, and some are so bizarre, so counterintuitive, so mind-bendingly strange that even after decades of studying them, physicists still struggle to wrap their heads around the implications. Did you know there's a black hole so massive it contains 66 billion times the mass of our sun? Did you know that if you fell into one, you'd experience time so differently that billions of years could pass in the outside universe while you experienced just moments? Did you know there might be microscopic black holes smaller than atoms that were created in the first fraction of a second after the Big Bang, and they could be passing through your body right now? By the end of this video, you'll understand why Stephen Hawking spent decades obsessed with black holes. You'll know why they're called the universe's ultimate recycling machines. You'll discover what happens at the event horizon, that point of no return where even light cannot escape. And you'll learn why black holes might hold the key to understanding the deepest mysteries of existence itself, the nature of space, time, information, and reality. Before we dive into this cosmic journey through the strangest objects in the universe, I need to ask you something. If you're ready to explore the darkest corners of space, if you're curious about the most extreme physics imaginable, please hit that like button and subscribe to Sleepy Copernicus. This channel is all about taking you on deep explorations of the cosmos, and your support means everything. Drop a comment below telling me, have you ever thought about what it would be like to fall into a black hole? Are you fascinated by them or terrified? Let me know where you're watching from and what time it is in your part of the world. Let's build a community of cosmic explorers together. Now get comfortable. This is going to be a long journey, over an hour of pure black hole knowledge, 169 facts that will take you from the basics to the cutting edge of theoretical physics. And I promise you, by fact 169, you'll never look at the night sky the same way again. Let's begin our descent into darkness. Fact 1. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape from inside it. The boundary of this region is called the event horizon, and once anything crosses that boundary, it's gone forever from our universe as far as we can observe. Let me explain what that actually means, because the popular image of black holes as cosmic vacuum cleaners sucking up everything around them is not quite right. Black holes don't suck. They don't reach out and grab things. What they do is warp space-time so extremely that the very geometry of space curves inward on itself. Imagine space-time as a rubber sheet. The classic analogy: put a bowling ball on the sheet and it creates a dip. Roll a marble near the bowling ball and the marble will curve toward it, following the curved surface. That's gravity in Einstein's general relativity. Mass curves space-time, and objects follow the curves. Now imagine making the bowling ball infinitely dense, compressed to a single point. The dip becomes infinitely steep. The rubber sheet curves so sharply that it forms a funnel shape that closes off from the rest of the sheet. That's a black hole. The event horizon is the point where the funnel becomes so steep that even if you tried to climb out at the speed of light, you'd still fall inward. It's not that the black hole is sucking you in, it's that space itself is falling inward faster than light can climb outward. Fact 2. The term black hole was coined by physicist John Archibald Wheeler in 1967 during a lecture, though the concept had been discussed for decades before under different names. Before Wheeler's catchy phrase caught on, These objects were called frozen stars or collapsed stars, or simply gravitationally completely collapsed objects, which is quite a mouthful. Wheeler's genius was recognizing that a short, evocative name would help popularize the concept, and he was right. The term black hole immediately captured the public imagination and has been used ever since. Wheeler himself later said he was inspired by the phrase Black Hole of Calcutta, referring to a dungeon where prisoners supposedly perished, though modern historians dispute that story. Regardless, the name stuck, and now when anyone anywhere in the world says black hole, everyone knows what they mean: a place where things go in and never come out. Fact 3. Black holes are predicted by Albert Einstein's theory of general relativity, published in 1915, though Einstein himself was skeptical they could actually exist in nature. General relativity describes gravity not as a force, but as the curvature of space-time caused by mass and energy. Einstein's field equations, 10 interrelated differential equations that describe how matter and energy curve space-time and how that curvature affects the motion of matter and energy, allow for solutions where space-time curves so extremely that an event horizon forms. But Einstein thought nature would find a way to prevent such extreme objects from forming. He was wrong. Nature not only allows black holes to form, it creates them routinely throughout the universe, millions or billions of them, as the natural end state of massive stars. Fact 4. The first solution to Einstein's equations describing a black hole was found by Karl Schwarzschild in 1916, just months after Einstein published General Relativity. Schwarzschild was serving in the German army during World War I, stationed on the Russian front, when he solved Einstein's equations for the case of a spherical non-rotating mass. His solution, now called the Schwarzschild metric, describes the geometry of space-time around a non-rotating black hole. He found that if you compress any mass within a certain radius which depends on the mass, the space-time curvature becomes so extreme that an event horizon forms. Tragically, Schwarzschild died later that year from a disease contracted on the front. He was only 42 years old. But his solution laid the foundation for all future black hole research. The radius he calculated, called the Schwarzschild radius, defines the size of the event horizon for a non-rotating black hole. For the Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it's about 9 millimeters. That means if you could somehow compress the Sun down to a sphere 6 kilometers across, or Earth down to a sphere less than 2 centimeters across, they'd become black holes. Fact 5. For a non-rotating, uncharged black hole, the event horizon radius is given by the formula R equals 2gm divided by c squared, where g is Newton's gravitational constant, m is the mass, and c is the speed of light. This formula, derived from the Schwarzschild solution, tells us the event horizon size for any mass. Let's break down what this means. The radius is directly proportional to the mass, so if you double the mass, you double the event horizon radius. A black hole with twice the mass of the Sun has an event horizon twice as large, about 6 kilometers in radius. A black hole with 1 million solar masses has an event horizon with a radius of about 3 million kilometers, roughly 4 times the radius of the Sun. The formula also shows that the event horizon radius depends on the speed of light squared in the denominator, which is an enormous number, 9 times 10 to the 16th meters squared per second squared. This means you need a lot of mass compressed into a small space to create an event horizon. The Sun's mass compressed to 3 kilometers, Earth's mass compressed to 9 millimeters. The amount of compression required is almost unimaginable. Fact 6. There are 4 main types of black holes based on mass: primordial black holes, stellar black holes, intermediate black holes, and supermassive black holes. This classification helps us understand the different ways black holes form and where we find them in the universe. Primordial black holes are hypothetical black holes that might have formed in the very early universe, fractions of a second after the Big Bang, from density fluctuations in the primordial plasma. If they exist, they could have any mass from microscopic, much smaller than an atom, up to thousands of solar masses. We haven't confirmed any primordial black holes exist yet, but they're a candidate for dark matter, the mysterious substance that makes up 85% of the matter in the universe. Stellar black holes form from the collapse of massive stars and typically have masses between about 5 and 100 times the mass of the Sun. These are the most common type we know about. Intermediate black holes are a mysterious middle category, with masses between about 100 and 100,000 solar masses. We've found a few candidates, but they're rare and not well understood. And supermassive black holes, the giants, have masses from about 100,000 solar masses up to tens of billions of solar masses. These monsters lurk at the centers of galaxies, including our own Milky Way. Fact 7. Stellar black holes form when massive stars, those with at least about 20 times the mass of the Sun, reach the end of their lives and undergo supernova explosions. Let me walk you through this process because it's one of the most dramatic events in the universe. A star spends most of its life fusing hydrogen into helium in its core. This fusion releases energy that creates an outward pressure, balancing the inward pull of gravity. The star is in equilibrium. Eventually, the hydrogen in the core runs out. If the star is massive enough, the core contracts and heats up until it's hot enough to fuse helium into carbon and oxygen. This process continues with heavier and heavier elements. Carbon fuses to neon and magnesium, neon to oxygen and magnesium, oxygen to silicon and sulfur, and finally silicon to iron. Each fusion stage releases less energy than the previous one and lasts for a shorter time. The final silicon burning stage lasts only about 1 day. At the end, the star has an onion-like structure with shells of different elements surrounding an iron core. Here's where the problem arises. Iron cannot be fused to release energy. Fusing iron actually requires energy input rather than releasing energy. So when the core becomes iron, no more fusion is possible. The outward pressure stops. Gravity wins. The core collapses. In less than a second, the iron core, roughly the size of Earth, collapses to about 20 kilometers across. Protons and electrons are squeezed together to form neutrons. The collapse happens so fast that the outer layers of the star don't have time to react. They're still falling inward when the core suddenly becomes incompressibly dense neutron matter and rebounds slightly, sending a shock wave outward. This shock wave blows the outer layers of the star into space in a spectacular supernova explosion, one of the brightest events in the universe, briefly outshining an entire galaxy. But the core remains. If the core's mass is between about 1.4 and 3 solar masses, it becomes a neutron star, an incredibly dense object made of neutrons packed together. But if the core's mass exceeds about 3 solar masses, not even neutron degeneracy pressure can hold it up against gravity. The collapse continues. Nothing can stop it. The core collapses to a point of infinite density, a singularity surrounded by an event horizon. A black hole is born. Fact 8. The dividing line between a neutron star and a black hole, approximately 3 solar masses for the remnant core, is called the Tolman-Oppenheimer-Volkoff limit, named after the physicists who calculated it in the 1930s. This limit is similar to the Chandrasekhar limit, which defines the maximum mass of a white dwarf star at about 1.4 solar masses, beyond which the white dwarf will collapse. The 2V limit tells us that neutron degeneracy pressure, the quantum mechanical pressure that prevents neutrons from occupying the same quantum state, can support a neutron star only up to a certain mass. Beyond that mass, gravity overwhelms the pressure and collapse to a black hole is inevitable. The exact value of the 2V limit is uncertain because we don't fully understand the properties of matter at the extreme densities found in neutron star cores. Current estimates place it somewhere between 2 and 3 solar masses, probably close to 3. This means that any stellar core more massive than about 3 suns will necessarily become a black hole. There's no escape, no other stable configuration is possible. Nature demands a black hole. Fact 9. Supermassive black holes, with masses millions to billions of times the sun's mass, are found at the centers of most large galaxies, including our Milky Way. The one in our galaxy, called Sagittarius A*, pronounced Sagittarius A star, has a mass of about 4.1 million solar masses and is located about 26,000 light-years from Earth. We've known for decades that something massive and compact sits at the center of the Milky Way, because we can observe stars orbiting it at enormous speeds. One star, called S2, orbits Sagittarius A*. Every 16 years it speeds up to about 5,000 kilometers per second, nearly 2% of the speed of light. By tracking S2 and other stars over years, and calculating the mass needed to make them orbit that fast, astronomers determined there must be about 4 million solar masses concentrated in a region smaller than our solar system. The only object that can be that massive and that compact is a black hole. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A*, showing the glowing ring of hot gas orbiting the black hole, with the black hole's shadow visible in the center. This image, years in the making, used a network of radio telescopes across the entire Earth working together as one giant telescope to achieve the angular resolution necessary to see such a small object so far away. It was definitive proof that our galaxy, like most large galaxies, hosts a supermassive black hole at its center. Fact 10. The most massive black hole ever discovered, as of 2025, is Ton 618, with an estimated mass of 66 billion solar masses. This is an almost incomprehensible amount of mass. 66 billion suns, all compressed within an event horizon that would be larger than the orbit of Pluto if it were in our solar system. Ton 618 is an ultramassive black hole powering a quasar, an extremely luminous active galactic nucleus where the black hole is actively feeding on surrounding matter. The infalling matter heats up to millions of degrees and radiates enormous amounts of energy across the electromagnetic spectrum. Ton 618 is so far away, about 10.4 billion light-years, that we're seeing it as it was 10.4 billion years ago when the universe was much younger. The fact that such a massive black hole existed so early in cosmic history is puzzling. How did it grow so large so quickly? Did it form from the collapse of a massive primordial gas cloud? Did smaller black holes merge together repeatedly? These are questions astronomers are still trying to answer, but Ton 618 stands as a monument to the universe's ability to create objects so extreme they challenge our understanding of physics. Fact 11. Black holes can spin, and spinning black holes are described by a different solution to Einstein's equations called the Kerr metric, discovered by Roy Kerr in 1963. A rotating black hole has some fascinating properties that non-rotating black holes don't have. First, the event horizon of a spinning black hole is smaller than it would be if the black hole weren't spinning, because the rotation creates additional effects that slightly counteract gravity. Second, a spinning black hole has an additional region outside the event horizon called the ergosphere, where space-time itself is dragged around by the black hole's rotation. Inside the ergosphere, it's impossible to stay still. You're forced to rotate with the black hole even if you're not orbiting it. You can still escape from the ergosphere, unlike from inside the event horizon, but you can't remain stationary. Third, the singularity inside a spinning black hole isn't a point like in a non-rotating black hole. Instead, it's a ring, called a ring singularity, where density becomes infinite. And fourth, the Kerr solution allows for bizarre theoretical possibilities like closed time-like curves, paths through space-time that loop back on themselves, essentially time travel to your own past. Whether closed time-like curves can actually exist in nature or whether some unknown physics prevents them is still debated. Fact 12. The rotation rate of a black hole is characterized by a dimensionless spin parameter A, which ranges from 0 for a non-rotating black hole to 1 for a maximally rotating black hole. The spin parameter is defined as E equals J divided by M, where J is the angular momentum, M is the mass, and we're using units where G equals C equals 1 for simplicity. A black hole with spin parameter A equals 1 is rotating as fast as theoretically possible. If you tried to spin it faster by dumping more angular momentum into it, the centrifugal effects would become so strong that the event horizon would disappear, exposing the singularity. This is called a naked singularity, and most physicists believe the cosmic censorship hypothesis, which states that singularities are always hidden behind event horizons and never naked. So A equals 1 is the maximum. Many observed black holes appear to be spinning quite rapidly, with spin parameters estimated between 0.5 and nearly 1. The supermassive black hole in the galaxy NGC 1365, for example, has been measured to have a spin parameter of about 0.84, meaning it's rotating at 84% of the maximum possible rate. This rapid rotation is probably acquired as the black hole swallows matter, which typically carries angular momentum. Fact 13. Black holes can be electrically charged, described by the Reissner-Nordström metric for a non-rotating charged black hole, or the Kerr-Newman metric for a rotating charged black hole. In principle, if you dropped a lot of electrons or protons into a black hole without an equal number of opposite charges, the black hole would acquire a net electric charge. However, in practice, astrophysical black holes are expected to be essentially neutral or very close to it. Because the universe contains both positive and negative charges in roughly equal amounts, and any significant charge on a black hole would quickly attract opposite charges from the surrounding environment, neutralizing it. If a black hole were positively charged, it would attract electrons and repel protons. Electrons would fall in, neutralizing the charge. If it were negatively charged, protons would fall in. So while charged black holes are possible in theory and are mathematically interesting, real black holes in the universe are almost certainly neutral, or so close to neutral that the charge is negligible. For this reason, astrophysicists usually ignore charge when modeling black holes and focus on mass and spin, the two properties that actually matter for real black holes. Fact 14. The no-hair theorem in black hole physics states that a black hole is completely characterized by only three externally observable properties: mass, electric charge, and angular momentum spin. Everything else about the matter that fell into the black hole, its composition, its chemical structure, whether it was made of stars or gas or planets or people, is lost. The black hole has no hair, meaning no distinguishing features beyond those three numbers. This is a profound statement about information loss. If you drop a grand piano and a bunch of hydrogen gas with the same total mass, charge, and angular momentum into a black hole, the resulting black hole will be absolutely identical in both cases. There's no way to tell what went in. All the information about the piano's wood, strings, keys, the manufacturer's label, the music that was played on it, all of that information is gone from our universe. This leads to deep problems in theoretical physics, particularly the black hole information paradox, which we'll discuss in more detail later. But the no-hair theorem, proven mathematically for the solutions to Einstein's equations, tells us that black holes are surprisingly simple objects despite being the most extreme environments in the universe. Fact 15. The event horizon of a black hole is not a physical surface or barrier. It's simply the boundary in space-time beyond which escape becomes impossible. If you were falling toward a black hole and you crossed the event horizon, you wouldn't feel anything special at that moment. There's no wall, no barrier, no sensation marking the transition. You'd just keep falling, but you'd have crossed a point of no return. Before crossing, if you fired your rockets hard enough, you could still escape. After crossing, no matter what you do, no matter how powerful your rockets, you will reach the singularity. The event horizon is the ultimate one-way boundary in the universe. Light emitted inside the event horizon directed outward toward the horizon will still move inward toward the singularity. That's how warped space-time is inside the horizon. Outward in space becomes inward toward the singularity. You can't escape, not because something is holding you back, but because all future paths through space-time lead to the singularity. Escape isn't just difficult, it's geometrically impossible. Fact 16. From the outside, if you watched someone fall into a black hole, you'd never actually see them cross the event horizon. Instead, you'd see them slow down and freeze, asymptotically approaching the horizon, but never quite reaching it, their image becoming redder and dimmer until they fade from view. This is due to extreme gravitational time dilation near the event horizon. Time, as measured by the falling person, passes normally for them. They fall through the horizon in a finite amount of their own time. But time, as measured by a distant observer, slows down near the horizon. From your perspective, watching from far away, their clock runs slower and slower as they approach the horizon, and at the horizon itself, their clock appears to stop entirely. So you see them approach the horizon, slow down, freeze, and fade. Their image is also red-shifted because the photons climbing out of the deep gravitational well lose energy, shifting to longer, redder wavelengths. Eventually, the photons are so red-shifted they become undetectable, and the person disappears from view. But from their own perspective, they fall through smoothly in finite time, perhaps seconds or minutes depending on the black hole's mass. This difference in perspectives the person falls through in finite proper time, but takes infinite time from an outside observer's perspective, is one of the strange consequences of general relativity. Fact 17. If you fell feet first into a stellar mass black hole, you'd be torn apart by tidal forces in a process called spaghettification long before you reach the event horizon. Tidal forces arise because gravity is stronger at your feet, which are closer to the black hole than at your head. The difference in gravitation and pull stretches your vertebrae. At the same time, gravity pulls you inward from all sides, compressing your horizontal for a stellar mass black hole with an event horizon perhaps 20 to 30 kilometers in radius. The tidal forces near the event horizon are enormous. Your body would be stretched into a long, thin strand like spaghetti, squeezed so thin horizontally that your atoms would be pulled apart, your molecules dissociated, your very atomic nuclei disrupted. You'd be killed and disintegrated well before crossing the horizon. Interestingly, for supermassive black holes this isn't the case, because the event horizon is so much larger, millions or billions of kilometers in radius. The tidal forces at the event horizon are actually quite gentle. You could cross the event horizon of a supermassive black hole and survive, at least initially. You'd feel nothing special as you crossed. Only deeper inside, as you fell toward the singularity, would tidal forces eventually become strong enough to kill you. So whether you'd be spaghettified before or after crossing the event horizon depends on the black hole's mass. Small black holes spaghettified before, giant black holes spaghettified after. Fact 18. At the very center of a black hole, according to general relativity, there is a singularity, a point where density becomes infinite, the curvature of space-time becomes infinite, and the laws of physics as we know them break down. The singularity is hidden inside the event horizon, invisible to the outside universe. For a non-rotating Schwarzschild black hole, the singularity is a single point, zero-dimensional, where all the black hole's mass is concentrated. For a rotating Kerr black hole, the singularity is a ring, one-dimensional, lying in the plane of the black hole's rotation. What actually happens at the singularity, we don't know. General relativity predicts infinite density and curvature, but when any theory predicts infinities, it's usually a sign that the theory is incomplete or breaks down in that regime. Most physicists believe that a correct theory of quantum gravity, which would combine general relativity with quantum mechanics, would replace the singularity with something else, perhaps a region of extremely high but finite density, perhaps something stranger. String theory, loop quantum gravity, and other candidate theories of quantum gravity all predict different things might happen at what general relativity says is a singularity. But until we have a confirmed theory of quantum gravity and a way to test it, the singularity remains a mystery, a place where our understanding of physics ends. Fact 19. According to quantum mechanics, in 1974, Stephen Hawking showed theoretically that black holes emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. Here's how it works. In quantum field theory, empty space isn't really empty. The vacuum is full of virtual particle-antiparticle pairs that constantly appear and disappear, borrowing energy from the vacuum for brief moments allowed by the Heisenberg uncertainty principle. Normally, these virtual pairs annihilate each other almost immediately and have no observable effect. But near the event horizon of a black hole, something different can happen. If a particle-antiparticle pair appears just outside the event horizon, one particle might fall into the black hole while the other escapes to infinity. To an outside observer, it looks like the black hole emitted a particle. This process is Hawking radiation. The black hole loses mass equal to the energy of the emitted particle, so the black hole slowly evaporates over time. For stellar mass or larger black holes, the Hawking radiation is incredibly faint, far too weak to detect, and the black hole gains mass from absorbing cosmic microwave background radiation much faster than it loses mass to Hawking radiation. But for very small black holes, hypothetical primordial black holes for instance, Hawking radiation could be significant. A black hole with the mass of a mountain would radiate at room temperature. A black hole with the mass of a small asteroid would glow white hot, and a black hole with the mass of a large ship would explode in a burst of gamma rays as it radiated away its final mass in a fraction of a second. Fact 20. The temperature of Hawking radiation is inversely proportional to the black hole's mass, given by the formula T equals h bar c cubed divided by 8 pi gmk, where h bar is the reduced Planck constant, c is the speed of light, g is the gravitational constant, m is the black hole's mass, and k is Boltzmann's constant. For a solar mass black hole, the temperature is about 60 nanokelvins, or 60 billionths of a degree above absolute zero. That's colder than the cosmic microwave background, which is about 2.7 Kelvin, so a solar mass black hole actually absorbs more radiation from the CMB than it emits via Hawking radiation. It grows rather than shrinking. For a supermassive black hole like Sagittarius A** with 4 million solar masses, the temperature is even lower, about 15 pikelvins or 15 trillionths of a degree above absolute zero. These black holes will take an unimaginably long time to evaporate. But for a small primordial black hole, say with the mass of the Moon, about 10 to the 22 kilograms, the Hawking temperature would be about 2.3 Kelvin, just slightly cooler than the CMB today, but warmer than the CMB will be in the far future. As the universe expands and cools, such a black hole would eventually evaporate, though it would take an enormously long time, roughly 10 to the 67 years, far longer than the current age of the universe. Fact 21. If black holes evaporate via Hawking radiation, they create an information paradox that has troubled physicists for decades. The paradox arises because Hawking radiation appears to be thermal, meaning it's random and carries no information about what fell into the black hole. In quantum mechanics, information is supposed to be conserved. If you know the quantum state of a system at one time, The laws of physics allow you to calculate the state at any other time. Information cannot be destroyed. But if a black hole evaporates into thermal radiation, what happens to the information about everything that fell into the black hole? It seems to be lost, violating a fundamental principle of quantum mechanics. This is the black hole information paradox. Stephen Hawking initially argued that information is indeed lost, which would require a modification of quantum mechanics. Others, including Leonard Susskind and Gerard Hooft, argued that information must somehow be preserved, perhaps encoded in the Hawking radiation and subtle correlations that we don't yet understand, or perhaps stored on the event horizon in a holographic manner. The debate has raged for decades. Recent work, including insights from string theory and the ADS-CSCFT correspondence, suggests that information is probably preserved, but exactly how remains one of the deepest unsolved problems in theoretical physics. Hawking himself eventually conceded that information is probably not lost, though the mechanism of preservation remains unclear. Fact 22. The total entropy of a black hole is proportional to the area of its event horizon, not its volume. This is called the Bekenstein-Hawking entropy, named after Jacob Bekenstein and Stephen Hawking, who developed the idea in the 1970s. The formula is S equals Ka divided by 4Lp squared, where S is entropy, K is Boltzmann's constant, A is the area of the event horizon, and Lp is the Planck length, about 1.6 times 10 to the negative 35 meters. This is a profound result. For normal objects, entropy is proportional to volume. More volume means more places to store information, more possible microstates, more entropy. But for black holes, entropy is proportional to area. This suggests that all the information about what's inside the black hole is somehow encoded on its surface, on the event horizon. This idea led to the holographic principle, which proposes that the description of a volume of space can be encoded on a boundary of that region, like a hologram encoding three-dimensional information on a two-dimensional surface. The holographic principle has become a cornerstone of modern theoretical physics, particularly in string theory and the study of quantum gravity, and it all started from understanding black hole entropy. Fact 23. A black hole can have an entropy that is enormous compared to any other object of similar mass. For example, a solar mass black hole has an entropy of about 10 to the 54 joules per Kelvin, vastly larger than the entropy of the Sun itself, which is about 10 to the 34 joules per Kelvin. This means a black hole represents an incredibly disordered state, the maximum entropy configuration for a given mass. In thermodynamics, systems tend to evolve towards states of higher entropy, so in some sense black holes are the ultimate endpoint of gravitational collapse, the highest entropy state that matter can reach. When a star collapses to a black hole, the entropy of the universe increases dramatically. This has implications for the arrow of time and the eventual fate of the universe. In the far future, after all stars have burned out and matter has either fallen into black holes or been dispersed by the expansion of space, the universe will be dominated by black holes, and eventually, after an unimaginable span of time, even the black holes will evaporate, leaving only a dilute sea of particles and radiation in an ever-expanding, ever-cooling cosmos. This is the heat death of the universe, the state of maximum entropy, where no further change is possible. Fact 24. The larger a black hole, the longer it takes to evaporate via Hawking radiation. The evaporation time is proportional to the cube of the black hole's mass. For a solar mass black hole, the evaporation time is about 10 to the 67 years. For a black hole the mass of Mount Everest, about 10 to the 15 kilograms, the evaporation time is about 10 to the 23 years, longer than the current age of the universe, but much shorter than for a stellar mass black hole. For a tiny primordial black hole with the mass of a modern aircraft carrier, about 100,000 tons or 10 to the 8th kilograms, the evaporation time is only about 100 years. Such a black hole, if it existed, and if one happened to be near us, would be evaporating right now, emitting radiation primarily in the form of gamma rays. Astronomers have searched for gamma ray signals from evaporating primordial black holes and haven't found any definitive detections, which puts constraints on how many such small black holes can exist in our cosmic neighborhood. Fact 25. It's theoretically possible that microscopic black holes could be created in high-energy particle collisions, such as those at the Large Hadron Collider, if certain theories like extra dimensions are correct. Some theories propose that in addition to the 3 spatial dimensions we experience, there may be additional compact dimensions that are too small to notice in everyday life, but which could affect physics at very high energies or very small scales. If extra dimensions exist, and if gravity can propagate through them, then the strength of gravity at small scales could be much higher than we think, and the energy required to create a black hole could be lower. In that case, colliding protons at energies achieved by the LHC, about 14 trillion electron volts, might create tiny black holes. These black holes would have masses roughly 10 to the negative 24 kilograms, far smaller than an atom, and they would evaporate via Hawking radiation in about 10 to the negative 26 seconds, essentially instantaneously. They decay into a shower of particles that could be detected. Searches have been conducted at the LHC for signatures of black hole production, and so far, none have been found. This doesn't mean extra dimensions don't exist, but it constrains their properties. And it's worth noting that even if the LHC did create microscopic black holes, they would be completely harmless, evaporating instantly into particles, not growing or swallowing anything. Fact 26. Black holes can merge together, and when they do, they release enormous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time itself. When 2 black holes orbit each other, they lose energy by emitting gravitational waves, causing their orbits to gradually shrink. As they spiral closer together, they orbit faster and emit stronger gravitational waves. In the final fraction of a second before they merge, they're orbiting each other hundreds of times per second, generating gravitational waves of incredible amplitude. When they finally collide and merge, forming a single larger black hole, the newly formed black hole is initially distorted, not perfectly spherical. It rings like a bell, oscillating and settling down into a stable spherical or spinning configuration, emitting more gravitational waves as it does so. The energy released during this process is staggering. In the first gravitational wave event ever detected, called GW150914, and observed on September 14, 2015 by the LIGO detectors, 2 black holes with masses of about 36 and 29 solar masses merged to form a 62 solar mass black hole. But wait, 36 plus 29 equals 65, not 62. Where did 3 solar masses worth of energy go? It was radiated away as gravitational waves in a fraction of a second. Using Einstein's famous equation E equals mc squared, 3 solar masses converts to about 5 times 10 to the 47 joules of energy, roughly equivalent to the entire mass energy of the sun converted to pure energy, released in just 1/5 of a second. At the peak of the merger, the gravitational wave luminosity, the power output in gravitational waves, exceeded the combined light output of all the stars in the observable universe. Let that sink in for a moment. This collision, happening over 1 billion light-years away, briefly outshone in gravitational wave energy every star, every galaxy, every quasar, everything luminous in the entire observable universe combined. That's the power of merging black holes. Fact 27. The gravitational waves from merging black holes were predicted by Einstein's general relativity over a century ago, but weren't detected until 2015 because they're incredibly weak by the time they reach Earth. Gravitational waves are distortions in space-time that propagate at the speed of light, stretching and squeezing space itself as they pass. but space is stiff. Even the most violent cosmic events produce gravitational waves that, by the time they reach us from distant galaxies, stretch and squeeze space by less than 1 part in 10 to the 21st. That means if the distance between Earth and the nearest star, about 4 light-years or 40 trillion kilometers, were being stretched by a gravitational wave, it would change by less than the width of a human hair. Detecting such tiny distortions requires exquisitely sensitive instruments. The Laser Interferometer Gravitational Wave Observatory, LIGO, consists of 2 facilities, one in Louisiana and one in Washington state, each with 2 4-kilometer-long arms arranged in an L shape. Laser beams travel up and down each arm, bouncing between mirrors, and the round-trip travel times are compared. When a gravitational wave passes, it stretches space in one direction and squeezes it in the perpendicular direction, changing the arm lengths by tiny amounts and causing the laser beams to arrive slightly out of phase. LIGO can detect length changes of about 1/10,000th the width of a proton. To put that in perspective, that's like measuring the distance from Earth to the nearest star to an accuracy of less than the width of a human hair. The engineering required to achieve this sensitivity is mind-boggling, involving vibration isolation, laser stabilization, ultra-high vacuum, precisely polished mirrors, and sophisticated data analysis. But it worked. On September 14, 2015, both LIGO detectors, separated by 3,000 kilometers, detected the same gravitational wave signal within 7 milliseconds of each other, the signature of 2 black holes merging over 1 billion light-years away. It was one of the most important scientific discoveries of the 21st century, confirming a century-old prediction and opening a completely new window on the universe. Fact 28. Since the first detection in 2015, LIGO and its partner detector Virgo in Italy have detected dozens of gravitational wave events, most from merging black holes but also from merging neutron stars and from black hole-neutron star mergers. Each detection provides information about the masses and spins of the objects, their distance from Earth, and sometimes their location on the sky. We're learning that black hole mergers are common, happening thousands of times per day throughout the observable universe. We're measuring the mass distribution of stellar black holes and finding some surprises, like black holes more massive than we expected from stellar evolution theory. We're testing general relativity in the strong field regime, where gravity is incredibly intense, and so far Einstein's theory passes every test with flying colors. And we're using gravitational waves as a new tool for cosmology, measuring the expansion rate of the universe independently of electromagnetic observations. Gravitational wave astronomy is still in its infancy, but it's already revolutionizing our understanding of black holes and the universe. Fact 29. When a black hole feeds on surrounding matter, it can become one of the brightest objects in the universe, forming what's called an active galactic nucleus, or AGN. Matter falling toward a black hole doesn't fall straight in. It has angular momentum, so it swirls around the black hole, forming an accretion disk, a flat rotating disk of gas and dust spiraling inward. Friction within the disk heats the material to millions of degrees. At these temperatures, the gas emits X-rays and other high-energy radiation. The inner part of the accretion disk, close to the event horizon, can reach temperatures of 10 million degrees or more, glowing brilliantly in X-rays. For supermassive black holes in the centers of galaxies, actively feeding on gas stars and other material, the accretion disk can be incredibly luminous, outshining the entire galaxy of hundreds of billions of stars. These are called quasars, short for quasi-stellar radio sources, because when they were first discovered in the 1960s, they looked like stars in optical images but emitted strong radio waves and had strange spectra. We now know quasars are powered by supermassive black holes actively accreting matter. The brightest quasars can be as luminous as 10 trillion suns, and they can be seen across the observable universe, billions of light years away. The light we see from distant quasars was emitted when the universe was young, giving us a window into the early cosmos. Fact 30. Black holes can launch jets, narrow beams of particles and energy that shoot out from the poles of the black hole at speeds close to the speed of light, extending for thousands or even millions of light years into space. These jets are among the most energetic phenomena in the universe. They're produced by complex interactions between the black hole, the accretion disk, and powerful magnetic fields. As matter spirals inward through the accretion disk, magnetic field lines threading through the disk can become twisted and amplified. Near the black hole, these twisted magnetic fields can accelerate particles to relativistic speeds and collimate them into narrow jets perpendicular to the disk. The exact mechanism is still not fully understood, but observations and simulations suggest that the rotation of the black hole itself, through a process called the Blandford-Zonagek mechanism, can extract rotational energy from the black hole and channel it into the jets. These jets carry enormous amounts of energy, sometimes containing more energy than the entire galaxy emits in starlight. When the jets slam into the intergalactic medium, they create huge lobes of radio-emitting plasma that can be larger than the galaxy itself. Radio telescopes can see these lobes, and they reveal the presence of an active supermassive black hole even when the galaxy is too distant for optical telescopes to see much detail. Fact 31. The most distant known quasar as of 2025 is J03131806, detected at a time when the universe was only about 670 million years old, less than 5% of its current age. This quasar is powered by a supermassive black hole with an estimated mass of about 1.6 billion solar masses. This is puzzling. How did such a massive black hole form so early in cosmic history? The universe at that time had only recently formed its first stars. There hadn't been much time for stars to live, die, leave black hole remnants, and for those black holes to grow by accretion and mergers into supermassive ones. The existence of billion solar mass black holes when the universe was less than a billion years old is a challenge for astrophysical models. Several scenarios have been proposed. Maybe the first stars were much more massive than typical stars today, hundreds of solar masses, and they collapsed directly into massive black holes that served as seeds for rapid growth. Maybe dense clusters of stars in the early universe collapsed directly into intermediate mass black holes that then merged and grew. Maybe some black holes formed directly from the collapse of massive gas clouds without going through a stellar phase at all, creating intermediate mass black holes right from the start. Or maybe black holes in the early universe accreted matter much faster than the standard Eddington limit, which normally sets the maximum rate at which a black hole can grow. Understanding how supermassive black holes formed so early is an active area of research, and observations of distant quasars like J03131806 are key to solving the puzzle. Fact 32. The Eddington limit is the maximum luminosity a black hole can sustain from accretion without blowing away the infalling matter. When matter falls into a black hole and heats up in the accretion disk, it emits radiation. That radiation exerts pressure on the surrounding gas, pushing it outward. If the luminosity is too high, the radiation pressure exceeds the gravitational pull and the infalling matter is blown away, shutting off the accretion. The Eddington limit depends on the black hole's mass. For a solar mass black hole, the Eddington luminosity is about 10 to the 31 watts, roughly 30,000 times the sun's luminosity. For a supermassive black hole of a billion solar masses, the Eddington luminosity is about 10 to the 40 watts, or about 3 trillion times the sun's luminosity. This limit sets the maximum rate at which a black hole can grow by accretion. If a black hole is accreting at the Eddington limit, it grows exponentially with an e-folding time, the time for its mass to increase by a factor of e of about 45 million years. Starting from a stellar black hole of 10 solar masses and growing at the Eddington limit, it would take about 800 million years to reach a billion solar masses. That's cutting it close for the early universe quasars, which is why astronomers think those black holes either started from larger seed masses or somehow exceeded the Eddington limit, perhaps through super-Eddington accretion in special circumstances. Fact 33. Some black holes appear to be accreting at or even above the Eddington limit in so-called ultraluminous X-ray sources, or ULX. These are extremely bright X-ray sources found in galaxies, often in regions of active star formation. Their luminosities exceed the Eddington limit for stellar mass black holes, which initially suggested they might be intermediate mass black holes, filling the gap between stellar and supermassive black holes. But detailed observations have revealed that many ULXs are actually stellar mass black holes, or even neutron stars accreting at super-Eddington rates. How can they exceed the Eddington limit? It turns out that if the accretion disk is geometrically thick, or if strong magnetic fields are present, the radiation can be beamed in certain directions rather than radiating isotropically, allowing higher accretion rates in the equatorial plane while still blowing material away from the poles. Or the accretion might be happening through channels or columns guided by magnetic fields, concentrating the inflow. The physics of super-Eddington accretion is complex and not fully understood, but observations of ULXs are giving us insights into these extreme regimes. Fact 34. The closest known black hole to Earth is Gaia BH1, located about 1,500 light-years away in the constellation Ophiuchus. Gaia BH1 is a stellar mass black hole with about 10 solar masses, and it's in a binary system with a Sun-like star that orbits it every 185 days. The black hole was discovered in 2022 using data from the European Space Agency's Gaia satellite, which precisely measures the positions and motions of billions of stars. Astronomers noticed that one star's motion showed a wobble, indicating it was orbiting an unseen companion. By measuring the orbital period and the star's velocity, they calculated the companion's mass and found it was too massive to be a neutron star, and showed no light emission, indicating it's a black hole. 1,500 light-years might sound far, and it is by human standards, but in cosmic terms it's practically in our backyard. There are probably hundreds of millions of stellar mass black holes in our Milky Way galaxy, but most are isolated, not in binary systems, and therefore invisible. They don't emit light themselves and don't have nearby matter to accrete and light up. They're just silent, invisible holes in space, drifting through the galaxy. Gaia BH1 is special because it has a companion star, allowing us to detect it through its gravitational influence. Fact 35. If a black hole passed through our solar system, the effects would depend on its mass and how close it came. A stellar mass black hole passing within a few astronomical units, the distance from Earth to the Sun, would gravitationally perturb the orbits of the planets, potentially ejecting some into interstellar space or causing collisions. If it passed very close to Earth, within 1,000,000 kilometers or so, tidal forces would be catastrophic, potentially disrupting Earth's structure. But the chances of a black hole passing that close are incredibly small. Space is vast, and even though there are many black holes in the galaxy, they're spread over enormous distances. The average distance between stars in our neighborhood of the Milky Way is about 4 light-years, and black holes are much rarer than stars. A close encounter with a black hole is extremely unlikely over the lifetime of the solar system. Still, it's a fun and terrifying thought experiment. If we saw a black hole approaching, we'd detect it through its gravitational effects on nearby stars and planets, giving us some warning. But there'd be nothing we could do to stop it or prevent the disaster. We'd just be along for the ride, hoping it passes far enough away to spare us. Fact 36. Intermediate mass black holes, with masses between 100 and 100,000 solar masses, are the most mysterious and least understood gravitational wave detections, and we have solid evidence for supermassive black holes in galactic centers from stellar orbits and direct imaging. But intermediate mass black holes have been elusive. A few candidates have been found, usually in the centers of globular clusters, dense spherical collections of stars orbiting galaxies, or in the centers of dwarf galaxies. One strong candidate is in the globular cluster Omega Centauri, where the motions of stars near the center suggest a black hole of about 40,000 solar masses. Another candidate is in the dwarf galaxy NGC 4395, which has an active nucleus suggesting a black hole of a few 100,000 solar masses, but confirmed detections are rare, and we don't know how common intermediate mass black holes are or how they form. They might be the result of repeated mergers of stellar mass black holes in dense star clusters. They might form from the direct collapse of massive stars in the early universe, or they might be the seeds that grew into supermassive black holes. Understanding intermediate mass black holes is important for understanding the full life cycle of black holes and the formation of supermassive black holes. Fact 37. Some scientists have proposed that primordial black holes, if they exist, could account for some or all of the mysterious dark matter that makes up 85% of the matter in the universe. Dark matter doesn't emit, absorb, or reflect light, so we can't see it directly. We infer its existence from gravitational effects, like the rotation curves of galaxies, gravitational lensing, and the distribution of matter in the universe, but we don't know what dark matter is made of. The leading candidates are exotic particles like WIMPs, weakly interacting massive particles or axions. But despite decades of searching, we haven't detected these particles. An alternative idea is that dark matter could be made of primordial black holes that formed in the very early universe from density fluctuations in the primordial plasma. If many primordial black holes with masses in certain ranges formed in the early universe, they'd be invisible, interact only gravitationally, and could account for dark matter. However, observations have placed strong constraints on this idea. Primordial black holes in certain mass ranges would cause observable effects, like microlensing of distant stars, distortions in the cosmic microwave background, or effects on the abundances of light elements formed in the Big Bang. These observations rule out primordial black holes as the dominant component of dark matter in most mass ranges, but there are still some allowed windows, particularly for black holes with masses around 10 to the 17 kilograms, about the mass of an asteroid, or around 10 to the 24 kilograms, about the mass of the Moon. In these ranges, the constraints are weaker, and primordial black holes could still contribute to dark matter. It's an ongoing area of research, and future observations might definitively rule out or support the primordial black hole dark matter hypothesis. Fact 38. If a primordial black hole with the mass of an asteroid, about 10 to the 17 kilograms, passed through Earth, it would punch straight through, entering on one side and exiting the other in less than a second. The black hole's event horizon would be only about 1/10 of a millimeter across, the size of a pinhead. As it passed through rock mantle and core, it would gravitationally attract and accrete some matter, but the amount would be negligible. Because the passage is so fast, the black hole wouldn't have time to swallow much. However, it would leave a narrow cylindrical tunnel through Earth, and the kinetic energy deposited along its path would heat the rock, possibly causing seismic effects, or even triggering volcanic activity if it passed through a geologically active region. The entry and exit points would see violent explosions as material compressed and heated by the black hole's passage was suddenly released. The total energy could be equivalent to a large nuclear bomb. If it passed through a populated area, the damage would be catastrophic locally, but globally, Earth would survive. The black hole would continue on its way through the solar system and eventually leave, having caused a brief but violent disturbance. Fortunately, if primordial black holes exist in the necessary numbers to account for dark matter, such an impact would be incredibly rare, perhaps once per billion years or longer for any given planet. Still, it's a dramatic scenario to contemplate. Fact 39. The Schwarzschild radius formula tells us some amusing things about everyday objects. If they were compressed to black holes, for example, if you compressed the entire Earth, mass about 6 times 10 to the 24 kilograms, into a black hole, the event horizon would have a radius of about 9 millimeters, roughly the size of a grape. The entire planet, all its oceans, continents, cities, 7 billion people, every living thing, all compressed into a sphere less than 2 centimeters across. If you compressed the sun, mass about 2 times 10 to the 30 kilograms, the event horizon would be about 3 kilometers in radius, 6 kilometers in diameter. That's roughly the size of a small mountain or a large city. The Sun, which currently has a radius of 700,000 kilometers, would be squeezed down to 6 kilometers, and if you compressed the entire Milky Way galaxy, with its roughly 200 billion stars, and a total mass of about 1.5 trillion solar masses, the event horizon would have a radius of about 1 light month, roughly twice the distance from the Sun to Neptune. That's still much smaller than the Milky Way's actual diameter of about 100,000 light years. But it's enormous compared to stellar mass black holes. These thought experiments show that the event horizon size scales linearly with mass, but the density needed to form a black hole, the average density within the event horizon, actually decreases for larger masses. A stellar mass black hole has a density exceeding that of atomic nuclei, but a supermassive black hole like the one in our galaxy has an average density, calculated as mass divided by the volume within the event horizon, less than that of water. For the most massive black holes, the average density is less than air. This doesn't mean the interior is empty or low density. It just means the event horizon is so large that if you averaged the mass over that volume, you'd get a low density. The actual density near the singularity is still infinitely high in classical general relativity. Fact 40. White holes are the theoretical time reversal of black holes. A black hole is a region where everything falls in and nothing can escape. A white hole would be a region where everything comes out and nothing can fall in. Just as you can't escape from inside a black hole's event horizon, you couldn't enter a white hole. Matter and energy would be ejected from a white hole, the opposite of a black hole accreting matter. White holes are allowed by the mathematics of general relativity as they're part of the extended Schwarzschild solution, but there's no evidence they exist in nature. Most physicists think white holes are purely mathematical curiosities, not real objects. One reason is that white holes would be highly unstable. Any tiny perturbation, like a single photon or particle approaching from outside, would be enough to collapse the white hole into a black hole. Additionally, white holes would require extremely special initial conditions in the universe, finely tuned in a way that seems unlikely. However, some theoretical physicists have speculated that white holes could be connected to black holes through wormholes, hypothetical tunnels through space-time, and that the Big Bang itself might be a kind of white hole, a point from which all matter and energy in the universe emerged. These ideas are highly speculative and not supported by evidence, but they're interesting to think about. Fact 41. Wormholes, also known as Einstein-Rosen bridges, are hypothetical structures connecting two separate points in space-time, potentially allowing shortcuts through space and time. In general relativity, the equations allow solutions where a black hole in one location is connected through a tunnel to a white hole or another black hole in a different location. possibly far across the universe or even in another universe. If you could travel through the wormhole, you'd enter at one mouth and emerge from the other, potentially bypassing vast distances. This has led to speculation that wormholes could be used for faster-than-light travel or even time travel. However, there are major problems. First, the wormholes that appear in solutions to Einstein's equations are unstable. They collapse so quickly that nothing could travel through them. Second, keeping a wormhole open would require exotic matter with negative energy density, something that violates the normal energy conditions we observe in nature. Quantum field theory allows negative energy densities in certain special situations like the Casimir effect, but whether enough negative energy could be gathered to stabilize a macroscopic wormhole is highly questionable. Most physicists are skeptical that traversable wormholes can exist, but the mathematics is tantalizing and the possibility, however remote, continues to inspire research and science fiction alike. Fact 42. If you could somehow survive falling into a black hole, and you looked back toward the outside universe as you fell, you would see the entire future history of the universe play out fast forward before your eyes. At least in principle, this is due to the extreme gravitational time dilation. From our perspective, time outside appears to speed up, from distant stars and galaxies will survive long enough, and if the black hole didn't evaporate first, you might see stars burning through their entire lifetimes, galaxies colliding and merging, the universe expanding, and eventually, trillions of years in the future, growing cold and dark as stars burn out and black holes evaporate. All of this would appear to happen in the brief moments before you reach the singularity. Of course, this is purely theoretical. In reality, you'd be killed by tidal forces and wouldn't be able to observe anything. And the light from the outside universe would be so blue-shifted and dim that seeing anything would be impossible. But as a thought experiment, it illustrates the strange effects of relativistic time dilation near black holes. Fact 43. The largest known stellar mass black holes discovered so far have masses around 80 to 100 times the mass of the Sun, pushing the upper limits of what stellar evolution models predict. One example is LB1, a black hole in a binary system in our galaxy, with an estimated mass of about 70 solar masses, though this measurement is controversial and may be revised. Theoretical models suggest that stars more massive than about 150 solar masses, called supermassive stars, should lose so much mass through stellar winds during their lives that by the time they die, their cores aren't massive enough to form black holes of 100 solar masses or more. But gravitational wave detections have found black holes with masses around 60 to 80 solar masses and possibly higher, challenging these models. Several possibilities could explain this. Maybe the stars formed in environments with low metallicity, meaning few elements heavier than hydrogen and helium, which would reduce the strength of stellar winds and allow more massive cores to form. Maybe some black holes formed from the direct collapse of very massive stars without going through a supernova, retaining more mass. Or maybe some of these massive black holes are the result of earlier mergers, where two smaller black holes merge to form a more massive one. Understanding the upper mass limit for stellar black holes and how these massive examples form is an active area of research. Fact 44. The presence of a supermassive black hole in the center of a galaxy can influence the evolution and structure of the entire galaxy through feedback mechanisms. When the central black hole is actively accreting, it emits enormous amounts of radiation and can launch powerful jets. This energy can heat the surrounding gas, preventing it from cooling and collapsing to form new stars. In effect, the black hole regulates star formation in the galaxy. Observations show a tight correlation between the mass of a galaxy's central supermassive black hole and properties of the galaxy's bulge, the dense central region of stars. This relationship, known as the m-sigma relation, links the black hole's mass to the velocity dispersion of stars in the bulge, a measure of their random motions. The existence of this correlation suggests that the black hole and the galaxy co-evolve, influencing each other's growth over cosmic time. The exact mechanisms are still being studied, but it's clear that supermassive black holes are not just passive inhabitants of galactic centers. They play an active role in shaping the galaxies they inhabit, controlling how much gas is available for star formation, and possibly even determining how large and massive the galaxy becomes. Fact 45. Some galaxies contain not one, but two supermassive black holes in their centers, orbiting each other. These binary supermassive black holes form when two galaxies merge, bringing their central black holes together. As the galaxies collide and merge over millions of years, the black holes sink toward the center of the newly formed galaxy due to dynamical friction, the gravitational drag from stars and gas. Eventually, the two black holes form a bound binary system orbiting each other. Over time, they emit gravitational waves, lose orbital energy, and spiral closer together. In the final stages, the gravitational wave emission becomes very strong, and the black holes merge in a massive event that releases huge amounts of energy in gravitational waves. We've detected mergers of stellar mass black holes, but merging supermassive black holes with millions or billions of solar masses would produce gravitational waves at lower frequencies than LIGO can detect. Future space-based detectors like LISA, the Laser Interferometer Space Antenna, planned for launch in the 2030s, will be sensitive to these lower frequencies and should detect supermassive black hole mergers. Ground-based observations have found a few candidate binary supermassive black holes by looking for periodic variations in quasar brightness, or by detecting two sets of broad emission lines in spectra, suggesting two accretion disks. But direct confirmation is difficult, and we don't yet know how common these systems are. Fact 46. If Earth were suddenly replaced by a black hole of equal mass, the orbits of the Moon and satellites would be unchanged, at least initially, because gravity at a distance depends only on mass, not on size or structure. This is a consequence of the shell theorem in Newtonian gravity, and is also true in general relativity for the region outside a spherical mass. As long as you're farther from the center than the original surface of the Earth, the gravitational pull you feel depends only on the total mass inside your radius. So if Earth became a 9 mm black hole, the Moon, orbiting at 384,000 kilometers, would continue orbiting as before. GPS satellites at 20,000 kilometers would continue orbiting. Even satellites in low Earth orbit at a few hundred kilometers would keep orbiting because they're still well outside the new event horizon. However, anything that was inside Earth's radius before the transformation, like buildings, people, the ground, would suddenly find itself falling toward the black hole. They'd fall inward, collide, form an accretion disk, heat up and radiate energy as they fell into the black hole. The result would be a tiny black hole surrounded by a rapidly accreting disk of Earth's former mass, glowing intensely in X-rays. The Moon would be bathed in this radiation, and any remaining satellites would likely be damaged, but dynamically the orbits wouldn't change. This thought experiment illustrates that gravity at a distance doesn't care about internal structure, only total mass. Fact 47. The innermost stable circular orbit, or ISICO, is the smallest radius at which an object can stably orbit a black hole without falling in. For a non-rotating Schwarzschild black hole, the ISICO is at 3 times the Schwarzschild radius, or 6 gm divided by c squared. Inside this radius, there are no stable circular orbits. You can orbit in an unstable spiral, but any perturbation will cause you to either fall into the black hole or escape to a larger radius. The icicle is important because it marks the inner edge of the accretion disk. Material in the disk can orbit stably down to the icicle, but once it crosses that radius, it rapidly plunges into the black hole, releasing a final burst of energy as it does so. For a maximally rotating Kerr black hole with spin parameter A equals 1, the icicle can be much closer, as close as the event horizon itself if you're orbiting in the same direction as the black hole's rotation, prograde orbits. This means a spinning black hole can have a more compact, hotter accretion disk, and can extract more energy from infalling matter before it crosses the event horizon. Measuring the properties of the inner accretion disk using X-ray observations of the iron emission line profiles or timing fluctuations allows astronomers to estimate the black hole's spin. Fact 48. The photon sphere is a spherical region around a black hole where gravity is so strong that photons, particles of light, can orbit the black hole in circular paths. For a non-rotating black hole, the photon sphere is at 1.5 times the Schwarzschild radius, or 3 gm divided by c squared. At this radius, light can travel in a circular orbit. Though the orbit is unstable, any slight perturbation will cause the photon to either spiral into the black hole or escape to infinity. The photon sphere is significant because it defines the boundary of the black hole's shadow, the dark region seen in images like those from the Event Horizon Telescope. Light emitted from outside the photon sphere can escape and reach distant observers. Light emitted from inside the photon sphere is either captured by the black hole or orbits multiple times before escaping, heavily distorted and redshifted. The edge of the shadow corresponds roughly to photons that graze the photon sphere. Because of gravitational lensing, the shadow appears larger than the event horizon itself. For a non-rotating black hole, the shadow has a radius of about 2.6 times the Schwarzschild radius. So a Schwarzschild black hole with an event horizon radius of 3 kilometers would cast a shadow with a radius of about 8 kilometers. This is why the Event Horizon Telescope images show a dark central region, the shadow, surrounded by a bright ring of light from the accretion disk. Fact 49. The color of light emitted by matter in an accretion disk depends on the temperature, which depends on how close the matter is to the black hole. Near the inner edge of the disk, close to the ESCO, temperatures can reach tens of millions of degrees, hot enough to emit X-rays. Farther out, the disk is cooler, emitting ultraviolet, optical, and infrared light. For stellar mass black holes, the peak emission is typically in X-rays. For supermassive black holes, the peak can be in the ultraviolet or optical. This is why different types of black holes are best observed at different wavelengths. Stellar mass black holes in X-ray binaries are bright X-ray sources. Active galactic nuclei powered by supermassive black holes emit across the spectrum but are particularly bright in the optical and ultraviolet. Observing black holes at multiple wavelengths gives a complete picture of the accretion process. Fact 50. Quasi-periodic oscillations, or QPOs, are rapid periodic variations in the brightness of X-ray light from black hole accretion disks, with periods ranging from milliseconds to seconds. These oscillations are thought to arise from various instabilities and resonances in the inner accretion disk, possibly related to the orbital motion of material near the ISCO, to precession of the disk, or to oscillations in the disk structure. Studying QPOs provides information about the mass and spin of the black hole and about the dynamics of matter in the strong gravitational field near the event horizon. QPOs have been observed in many X-ray binaries containing black holes or neutron stars, and they're one of the ways astronomers can distinguish between black holes and neutron stars, as the two types of objects produce different QPO patterns. Fact 51. The frame dragging effect, also called the lens thirring effect, occurs near any rotating mass but is especially strong near spinning black holes. Frame dragging is the phenomenon where a rotating mass drags space-time around with it, forcing nearby objects to rotate in the same direction. For a spinning black hole, space-time inside the ergosphere is dragged so strongly that nothing can remain stationary. Even light beams are dragged around. For objects orbiting close to a spinning black hole, their orbital planes precess, rotating over time due to frame dragging. This effect has been measured for satellites orbiting Earth, confirming a prediction of general relativity, but the effect near Earth is tiny. Near a black hole, frame dragging is extreme and has observable consequences for the shapes and motions of accretion disks and jets. Observations of X-ray binaries and AGN provide evidence for frame dragging, and measuring its effects allows astronomers to determine the black hole's spin. Fact 52. The Penrose process is a theoretical mechanism by which energy can be extracted from a rotating black hole. Proposed by physicist Roger Penrose in 1969, the process works as follows. An object falls into the ergosphere, the region outside the event horizon, where space-time is dragged around by the black hole's rotation. Inside the ergosphere, the object splits into two parts. One part falls into the black hole, crossing the event horizon. The other part escapes to infinity. If the process is arranged correctly, the escaping part can have more energy than the original object, with the extra energy coming from the rotational energy of the black hole. In effect, the black hole's spin is reduced, and that rotational energy is transferred to the escaping particle. The Penrose process is a way to extract energy from a black hole, and it's thought to be related to the formation of jets in active galactic nuclei. A variant called the Blandford-Zinejek process, which involves magnetic fields threading through the ergosphere, is believed to be the mechanism that powers relativistic jets from spinning black holes. These processes demonstrate that black holes are not just sinks of energy. They can be sources of energy, engines that power some of the most luminous phenomena in the universe. Fact 53. If advanced civilizations exist, they might build structures around black holes to harness their energy. One idea is a Dyson sphere, a hypothetical megastructure that encompasses a star to capture its energy, but adapted for black holes. You could build a shell around a black hole to capture the energy from its accretion disk and Hawking radiation, though for stellar mass or larger black holes, Hawking radiation is negligible. A more practical idea might be to use the Penrose process or Blandford-Zinejek mechanism to extract rotational energy from a spinning black hole. You could imagine an advanced civilization building massive structures in orbit around a black hole, using the intense gravitational field for energy production, computation, or even as a means of interstellar travel by gravitational slingshot. Black holes might be valuable resources in a spacefaring civilization's economy. Some futurists have even suggested that extremely advanced civilizations might create artificial black holes as power sources or use natural black holes as the ultimate garbage disposal, dumping waste into them. These are speculative ideas, but they illustrate that black holes, despite their reputation as destructive forces, could potentially be useful. Fact 54. Time dilation near a black hole is so extreme that it could theoretically be used for time travel to the future. If you orbited close to the event horizon of a supermassive black hole where tidal forces wouldn't tear you apart, time would pass much more slowly for you than for people far from the black hole. You could orbit for what feels like a few years, then return home to find that centuries or millennia have passed on Earth. This is one-way time travel to the future, allowed by relativity. It's not science fiction, it's real physics. The closer you orbit to the event horizon, the stronger the time dilation. For example, in the movie Interstellar, the characters visit a planet orbiting close to a supermassive black hole, and 1 hour on the planet equals 7 years outside. This is exaggerated for dramatic effect, but it's based on real physics. The time dilation factor near a black hole can be calculated from the metric, and it increases steeply as you approach the event horizon, diverging to infinity exactly at the horizon. So if you wanted to travel far into the future, you could theoretically orbit near a black hole for a while, then return to the outside universe. The challenge would be surviving the environment, avoiding falling in, and having enough fuel to escape the black hole's gravity well when you're done. But in principle, it's possible. Fact 55. Black holes might be connected to the multiverse, a hypothetical collection of multiple universes. Some interpretations of general relativity and quantum mechanics suggest that black holes could be gateways to other universes, or that the interiors of black holes might contain entire universes themselves. One idea, proposed by physicist Lee Smolin, is cosmological natural selection, where new universes are born inside black holes. When a black hole forms and reaches the singularity, instead of infinite density, quantum effects might cause a bounce, creating a new expanding universe inside the black hole, disconnected from our universe. This new universe would have its own space, time, and physical laws, possibly slightly different from ours. If many black holes form, many new universes are born, and those universes would inherit properties from the parent universe, leading to a kind of evolutionary process where universes that produce many black holes are more common. This is highly speculative and not testable with current technology, but it's an intriguing idea that connects black holes to the deepest questions about existence and the nature of reality. Other ideas involve black holes being connected to white holes in other universes through wormholes, or the holographic principle suggesting that our entire universe might be encoded on the event horizon of a higher dimensional black hole. These ideas stretch the boundaries of science into philosophy, but they remind us that black holes are still profoundly mysterious objects. Fact 56. The cosmic censorship hypothesis, proposed by Roger Penrose in 1969, states that singularities are always hidden inside event horizons and can never be observed from the outside, meaning naked singularities cannot exist in nature. A naked singularity would be a region of infinite density and curvature visible to the outside universe, without an event horizon to hide it. If naked singularities existed, they would break the predictability of physics because the equations of general relativity become undefined at singularities. Anything could emerge from a naked singularity, and we couldn't predict what would happen. Most physicists believe cosmic censorship is true, that nature always conspires to prevent naked singularities from forming. When a massive star collapses, an event horizon forms before the singularity, ensuring the singularity is hidden. When black holes are spun up by accreting matter, they can't spin faster than the maximum rate without the event horizon disappearing, and some mechanism prevents them from reaching that limit. However, cosmic censorship has not been proven rigorously for all possible situations, and some exotic scenarios in theoretical physics might allow naked singularities in special circumstances. Most physicists suspect that quantum gravity effects, which we don't yet fully understand, will prevent naked singularities even in those cases. But until we have a complete theory of quantum gravity, cosmic censorship remains a conjecture, albeit a very well-motivated one. Fact 57. If you fell into a black hole from your perspective, you would reach the singularity in a finite amount of proper time, the time measured by your own clock. For a solar mass black hole, you'd reach the singularity in about 10 microseconds after crossing the event horizon, barely any time at all. For a supermassive black hole like Sagittarius, a star with 4 million solar masses, you'd have about 16 seconds after crossing the horizon before hitting the singularity. That's more time, but still not much. During this time, tidal forces would be stretching and compressing you, spaghettification would be underway, and you'd be approaching a region where the curvature of space-time becomes infinite and the laws of physics break down. The experience would be brief and fatal. From the outside, however, an observer would never see you reach the singularity. They wouldn't even see you cross the event horizon. Due to time dilation, you'd appear to slow down and freeze at the horizon, your image fading and redshifting until it became undetectable. This difference in perspectives, finite proper time for the infalling observer versus infinite coordinate time for the external observer, is one of the most mind-bending aspects of black hole physics. Fact 58. Black holes can have temperature, and that temperature is inversely proportional to their mass. We discussed Hawking radiation earlier, and the temperature associated with Hawking radiation defines the black hole's temperature. A stellar mass black hole has a temperature of about 60 nanokelvins, far colder than the cosmic microwave background. But a microscopic primordial black hole could have a temperature of billions of degrees, hotter than the core of the sun. As a black hole evaporates and loses mass through Hawking radiation, its temperature increases. The smaller it gets, the hotter it gets, and the faster it evaporates. This leads to a runaway process. In the final moments of a black hole's evaporation, when it's down to a mass comparable to a mountain or a large asteroid, it would be radiating at an incredible rate, its temperature soaring to trillions of degrees. The final explosion, as the last bit of mass converts to radiation in a fraction of a second, would release a burst of energy equivalent to millions of nuclear bombs. If such an event happened nearby, it would be detectable across the universe. Astronomers have searched for these final evaporation bursts and haven't found any, which tells us either primordial black holes don't exist in large numbers, or they're not evaporating in our cosmic neighborhood right now. Fact 59. Black holes can act as gravitational lenses, bending the light from objects behind them and creating multiple images, arcs, or rings of light. This effect, called gravitational lensing, occurs because the black hole's gravity warps space-time, and light follows the curves of space-time. If a distant star or galaxy is directly behind a black hole from our perspective, the black hole's gravity bends the light around it, and we can see the background object as a ring of light surrounding the black hole. This is called an Einstein ring. If the alignment isn't perfect, we see arcs or multiple distorted images. Gravitational lensing by black holes is used to study both the black holes themselves and the background objects being lensed. It's also used to search for isolated black holes that aren't in binary systems and don't have accretion disks. If a black hole passes in front of a distant star, the star's light will brighten and distort in a characteristic way, a microlensing event. By monitoring millions of stars and looking for these temporary brightening events, astronomers can detect black holes that would otherwise be invisible. Several candidates have been found this way, though distinguishing black holes from other compact objects like neutron stars or brown dwarfs can be challenging. Fact 60. The Event Horizon Telescope collaboration, which produced the first images of black holes, used a technique called Very Long Baseline Interferometry, or VLBI, to achieve the angular resolution necessary to see the shadow of a black hole. VLBI works by combining observations from multiple radio telescopes spread across the Earth, effectively creating a virtual telescope as large as the planet. The farther apart the telescopes, the higher the resolution. For the Event Horizon Telescope, 8 telescopes on 4 continents, from the South Pole to Greenland, observed simultaneously. The data from each telescope was recorded with extremely precise timing using atomic clocks, then later combined and processed to create an image. The angular resolution achieved was about 20 microarcseconds, which is equivalent to seeing a grapefruit on the moon from Earth. This incredible resolution was necessary because even though supermassive black holes are enormous in absolute size, they're so far away that they appear tiny in the sky. Sagittarius A star, our galaxy's black hole, has an event horizon about 26 million kilometers across, but at a distance of 26,000 light-years, it subtends an angle of only about 50 microarcseconds. That's smaller than a donut on the Moon, as seen from Earth. The M87 black hole, 55 million light-years away, is much more massive and therefore has a much larger event horizon, about 40 billion kilometers across, but its greater distance makes it appear a similar angular size. Both are at the limit of what can be resolved even with an Earth-sized telescope array. Fact 61. The first black hole image, released by the Event Horizon Telescope in April 2019, was of the supermassive black hole in the galaxy M87, called M87 star. The image shows a bright ring of emission from the accretion disk surrounding a dark central shadow. The shadow is about 2.5 times larger than the event horizon itself due to gravitational lensing effects. The bright ring is asymmetric, brighter on one side than the other due to Doppler boosting. Material in the accretion disk orbits the black hole at a significant fraction of the speed of light. The side of the disk rotating toward us appears brighter because the light is blue shifted and beamed in our direction. The side rotating away appears dimmer because the light is red shifted and beamed away from us. The image confirmed many predictions of general relativity and provided the first direct visual evidence of an event horizon. It was a triumph of observational astronomy, computational imaging, and theoretical physics. The data used to create the image was so massive, about 5 petabytes, that it couldn't be transmitted over the internet. Instead, hard drives had to be physically shipped from the telescopes to central processing facilities. Creating the image required years of work by hundreds of scientists and the development of new algorithms to combine the data and extract a coherent image from noisy observations. Fact 62. The second black hole image released by the Event Horizon Telescope in May 2022 was of Sagittarius A star, the black hole at the center of our Milky Way galaxy. This image was much more difficult to obtain than the M87 image, even though Sagittarius A star is much closer to us. The reason is that the accretion flow around Sagittarius A star is much more turbulent and variable. Material orbits Sagittarius A star in just minutes compared to days or weeks for M87 star, because Sagittarius A star is much less massive and therefore much smaller. This means the appearance of the accretion disk changes on timescales of minutes. During the hours of observation needed to collect enough data, the structure of the disk changed significantly, blurring the image. To overcome this, the scientists developed new techniques to average over the variability and extract the persistent features. The resulting image shows a similar bright ring with a dark shadow, confirming that Sagittarius A star is indeed a black hole and that its appearance matches theoretical predictions. Having images of two very different black holes, one about 1,500 times more massive than the other in two very different environments, provides strong evidence that black holes behave as general relativity predicts regardless of their mass or location. Fact 63. Some physicists have proposed alternatives to black holes called gravastars, gravistar being short for gravitational vacuum star. A gravistar would be a theoretical object similar to a black hole in that it has intense gravity and can form from gravitational collapse, but instead of having an event horizon and a singularity, it would have a surface made of exotic matter with negative pressure, similar to dark energy. This exotic matter would halt the collapse just before an event horizon forms, creating a stable object without a singularity. The interior would be a bubble of vacuum energy, essentially a region of dark energy surrounded by a thin shell of ultra-dense matter. From the outside, a gravistar would look almost identical to a black hole, and most observations couldn't distinguish between them. However, gravastars are highly speculative. There's no direct evidence they exist, and it's unclear whether the exotic matter to support them can actually exist in nature. Most astrophysicists think black holes are the correct description, but gravastars represent an interesting alternative that avoids some of the conceptual problems of singularities and information loss. Fact 61. The first black hole image, released by the Event Horizon Telescope in April 2019, was of the supermassive black hole in the galaxy M87, called M87 star. The image shows a bright ring of emission from the accretion disk surrounding a dark central shadow. The shadow is about 2.5 times larger than the event horizon itself due to gravitational lensing effects. The bright ring is asymmetric, brighter on one side than the other. Due to Doppler boosting, material in the accretion disk orbits the black hole at a significant fraction of the speed of light. The side of the disk rotating toward us appears brighter because the light is blue-shifted and beamed in our direction. The side rotating away appears dimmer because the light is red-shifted and beamed away from us. The image confirmed many predictions of general relativity and provided the first direct visual evidence of an event horizon. It was a triumph of observational astronomy, computational imaging, and theoretical physics. The data used to create the image was so massive, about 5 petabytes, that it couldn't be transmitted over the internet. Instead, hard drives had to be physically shipped from the telescopes to central processing facilities. Creating the image required years of work by hundreds of scientists and the development of new algorithms to combine the data and extract a coherent image from noisy observations. Fact 62. The second black hole image released by the Event Horizon Telescope in May 2022 was of Sagittarius A star, the black hole at the center of our Milky Way galaxy. This image was much more difficult to obtain than the M87 image, even though Sagittarius A star is much closer to us. The reason is that the accretion flow around Sagittarius A star is much more turbulent and variable. Material orbits Sagittarius A star in just minutes compared to days or weeks for M87 star, because Sagittarius A star is much less massive and therefore much smaller. This means the appearance of the accretion disk changes on timescales of minutes. During the hours of observation needed to collect enough data, the structure of the disk changed significantly, blurring the image. To overcome this, the scientists developed new techniques to average over the variability and extract the persistent features. The resulting image shows a similar bright ring with a dark shadow, confirming that Sagittarius A star is indeed a black hole and that its appearance matches theoretical predictions. Having images of two very different black holes, one about 1,500 times more massive than the other in two very different environments, provides strong evidence that black holes behave as general relativity predicts regardless of their mass or location. Fact 63. Some physicists have proposed alternatives to black holes called gravastars, gravistar being short for gravitational vacuum star. A gravistar would be a theoretical object similar to a black hole in that it has intense gravity and can form from gravitational collapse, but instead of having an event horizon and a singularity, it would have a surface made of exotic matter with negative pressure, similar to dark energy. This exotic matter would halt the collapse just before an event horizon forms, creating a stable object without a singularity. The interior would be a bubble of vacuum energy, essentially a region of dark energy surrounded by a thin shell of ultra-dense matter. From the outside, a gravistar would look almost identical to a black hole, and most observations couldn't distinguish between them. However, gravastars are highly speculative. There's no direct evidence they exist, and it's unclear whether the exotic matter needed to support them can actually exist in nature. Most astrophysicists think black holes are the correct description, but gravastars represent an interesting alternative that avoids some of the conceptual problems of singularities and information loss. Fact 64. Another alternative to traditional black holes is the fuzzball proposal from string theory. What we think of as the event horizon and the empty space inside it is actually replaced by a highly excited, tangled configuration of strings and branes, the fundamental objects in string theory. The fuzzball would have no interior, no singularity, and no information paradox, because the information about infalling matter would be encoded in the complex configuration of strings on the fuzzball's surface. From a distance, A fuzzball would look like a black hole with the same mass, charge, and spin, but it would have structure at the Planck scale, far too small to observe with any foreseeable technology. Fuzzballs are an attempt to resolve the black hole information paradox by fundamentally changing what a black hole is at the quantum level. Like gravistars, fuzzballs are speculative and not yet supported by direct evidence, but they represent how physicists are thinking about black holes in the context of quantum gravity. Fact 65. Black holes can evaporate completely over extremely long timescales through Hawking radiation, but the final fate of an evaporating black hole is uncertain. As the black hole shrinks, its temperature increases and it radiates faster. In the final moments, when the black hole is down to the Planck mass, about 22 micrograms, which is the mass where quantum gravitational effects become dominant, the black hole's properties become impossible to predict with our current understanding of physics. Does it disappear entirely, leaving behind only radiation? Does it leave a Planck scale remnant, a tiny stable object that can't evaporate further? Does something else happen, perhaps a transition to a different kind of object or a quantum tunneling event? We don't know. Understanding the endpoint of black hole evaporation requires a theory of quantum gravity that we don't yet have. This is one of the key questions that a successful theory of quantum gravity, whether string theory, loop quantum gravity, or something else, will need to answer. Fact 66. The area theorem, proved by Stephen Hawking in the early 1970s, states that the total area of event horizons can never decrease over time in classical general relativity. If two black holes merge, the area of the final black hole's event horizon is always greater than or equal to the sum of the areas of the two original event horizons. If a black hole accretes matter, its event horizon area increases. Even if a black hole doesn't grow, its area stays constant. It can never shrink. This theorem is remarkably similar to the second law of thermodynamics, which states that the total entropy of a closed system can never decrease. This similarity led Bekenstein and Hawking to propose that black hole area is actually a form of entropy, leading to the Bekenstein-Hawking entropy formula we discussed earlier. However, when quantum effects are included, black holes can evaporate via Hawking radiation, and their event horizon area does decrease over time. This seems to violate the area theorem, but the resolution is that the entropy radiated away in the Hawking radiation is greater than the decrease in black hole entropy. So the total entropy of the black hole plus the radiation still increases, preserving the second law of thermodynamics. This interplay between black hole thermodynamics and quantum mechanics is one of the deepest connections in theoretical physics. Fact 67. If you could somehow extract information from inside a black hole, you'd violate causality and potentially create paradoxes. Information from inside the event horizon can't reach the outside universe because nothing, not even light, can escape. So any information about what happened inside is lost to external observers. This is part of what makes the information paradox so troubling. In quantum mechanics, information is conserved, meaning the quantum state of a system evolves unitarily and can in principle be reconstructed. But if information falls into a black hole and the black hole later evaporates into thermal radiation that carries no information about what fell in, the information seems to be lost, violating unitarity. Some physicists have proposed that information is encoded on the event horizon in a holographic manner and gradually released in subtle correlations in the Hawking radiation. Over the black hole's lifetime, others suggest that information might be released in a burst during the final moments of evaporation. Still others think the paradox indicates a need for new physics beyond quantum mechanics and general relativity. This is an active area of research, and recent insights from quantum information theory, holography, and the ADSES-CFT correspondence have made progress, but a complete resolution is still being debated. Fact 68. Black holes can have quantum properties that just mass, charge, and states don't affect the classical properties of the black hole, but could encode information about what fell in. This quantum hair would be incredibly difficult to detect or measure, but its existence could resolve the information paradox by providing a way for information to be stored and later released. The exact nature of quantum hair, and whether it actually exists in nature, is still being worked out theoretically. If it does exist, it would represent a modification or extension of the no-hair theorem at the quantum level, adding a new layer of complexity to our understanding of black holes. Fact 69. The holographic principle, inspired by black hole thermodynamics, proposes that all the information contained in a volume of space can be represented by information on the boundary of that region. In other words, a three-dimensional region can be fully described by a two-dimensional surface surrounding it, like a hologram encoding three-dimensional images on a two-dimensional film. This principle arose from the observation that black hole entropy is proportional to the area of the event horizon, not the volume inside. If the maximum entropy of a region depends on its boundary area, then in some sense the boundary contains all the information about the interior. The holographic principle has been explored extensively in string theory, particularly through the ADS-CFT correspondence, which provides a concrete example of holography. In this correspondence, a theory of gravity in a five-dimensional anti-de Sitter space is equivalent to a four-dimensional quantum field theory without gravity on the boundary. This duality has been used to study quantum properties of black holes and has provided insights into quantum gravity, even though our universe is not anti-de Sitter space. The holographic principle suggests that space and even gravity might be emergent phenomena arising from more fundamental quantum information on a lower dimensional boundary. This is a radical rethinking of the nature of reality, and it all started from trying to understand black hole entropy. Fact 70. Black holes can rotate at nearly the speed of light at their event horizons. For a maximally spinning black hole with spin parameter a equals 1, the event horizon is rotating at the speed of light at the equator. Material orbiting close to such a black hole, in the innermost stable circular orbit, would be moving at a significant fraction of light speed, perhaps 30 to 40% of c. At these speeds, relativistic effects are extreme. Time dilation is significant. Kinetic energy is huge. Material in the accretion disk would be heated to incredibly high temperatures by friction and compression, emitting X-rays and gamma rays. The jets launched from spinning black holes, powered by the Blandford-Zanajek mechanism, can accelerate particles to velocities exceeding 99.9% of the speed of light, creating beams that extend for millions of light years into intergalactic space. These ultra-relativistic jets are among the most energetic phenomena in the universe, and they're powered by the rotation of black holes. Fact 71. If the universe is infinite, there are likely an infinite number of black holes. Even if black holes are rare by volume, if space extends infinitely in all directions, there would be infinitely many of them. Moreover, if the multiverse hypothesis is correct, and there are infinitely many separate universes, each potentially containing black holes, then the total number of black holes across all universes would be infinite. Even in our observable universe, which is finite because we can only see out to a distance determined by the speed of light and the age of the universe, there are estimated to be at least 100 million stellar mass black holes in the Milky Way alone, and probably hundreds of billions of galaxies in the observable universe, each with millions of stellar black holes and a supermassive black hole at its center. Counting them all, we might have something like 10 to the 19 or 10 to the 20 black holes in the observable universe. That's 10 billion black holes, and that's just what we can see. The universe beyond our observable horizon could contain vastly more, perhaps infinitely many. Fact 72. Some black holes might be older than the stars. Primordial black holes, if they exist, would have formed in the first fraction of a second after the Big Bang, making them about 13.8 billion years old as the universe itself. The first stars didn't form until a few 100 million years after the Big Bang, so primordial black holes would predate all stars, all galaxies, all planets, all life. They would be relics from the universe's infancy, tiny time capsules preserving information about the conditions in the earliest moments of cosmic history. Finding and studying primordial black holes would give us insights into the Big Bang, inflation, and the physics of the early universe that we can't get any other way. Unfortunately, they're also incredibly hard to detect if they exist, because they'd be small and isolated, emitting no light unless they're accreting matter or evaporating, and even then the signals would be faint. Fact 73. Black holes can exist in higher dimensional spacetimes, and their properties are different from black holes in our four-dimensional spacetime of 3 space dimensions plus 1 time dimension. In string theory and other theories of extra dimensions, black holes can exist in spaces with 4, 5, 10, or even 11 dimensions. The geometry of these higher dimensional black holes is more complex. In 4 spacetime dimensions, the event horizon is a 2-dimensional sphere. In 5 spacetime dimensions, it's a 3-dimensional sphere, and so on. Higher dimensional black holes can have exotic topologies, like black rings, which are event horizons, shaped like a donut rather than a sphere. These black rings are unstable in 4 dimensions but can be stable in 5 or more dimensions. Studying higher dimensional black holes helps physicists understand string theory and quantum gravity, and it also provides insights into the behavior of black holes in our own 4-dimensional universe by revealing which properties are universal and which depend on the number of dimensions. Fact 74. Black holes are the most efficient engines for converting mass into energy that we know of in the universe. When matter falls into a black hole, up to about 42% of its rest mass energy can be converted into radiation and jets through various processes, especially for maximally spinning black holes. In contrast, nuclear fusion in stars converts only about 0.7% of mass to energy, and nuclear fission converts even less. Matter-antimatter annihilation converts 100% of mass to energy, but antimatter is rare in the universe, and creating it requires energy. Black hole accretion is therefore the most efficient naturally occurring energy conversion process. This is why active galactic nuclei and quasars powered by black holes are so incredibly luminous. A supermassive black hole accreting just a few solar masses per year can output the energy of trillions of suns. If humanity ever reaches a technological level where we can harness black holes, they could be the ultimate power source, far surpassing fusion reactors or any other energy technology we can imagine. Fact 75. The Schwarzschild radius sets the scale below which an object must be compressed to become a black hole, but even if an object is compressed below this radius, it doesn't instantly become a black hole. The formation of an event horizon is a global property of the space-time geometry, not a local property. During gravitational collapse, as matter falls inward and density increases, the event horizon forms when the matter crosses the Schwarzschild radius and the geometry of space-time becomes such that outward-directed light rays are bent back inward. From the perspective of an outside observer, the event horizon appears to form just before the surface of the collapsing matter crosses the Schwarzschild radius, and it forms at the Schwarzschild radius itself. From the perspective of the infalling matter, there's no moment when the event horizon appears. The matter just continues falling inward, eventually reaching infinite density at the singularity in finite proper time. The event horizon is a null surface, a boundary made of outgoing light rays that are just barely staying in place, neither falling inward nor escaping outward. It's a beautiful and subtle concept that took decades to fully understand after Einstein published general relativity. Fact 76. Black holes don't care what falls into them, whether it's hydrogen gas, iron, antimatter, dark matter. If it interacts gravitationally, photons, neutrinos, or even other black holes. Everything that crosses the event horizon contributes to the black hole's mass. The black hole doesn't distinguish between types of matter. It only cares about mass, energy, which is equivalent to mass via E equals mc squared, charge, and angular momentum. This universality is part of what makes black holes so simple yet so profound. They're the ultimate equalizer. Gold and garbage, people and planets all become indistinguishable once they've fallen in. The black hole's properties are determined solely by the total mass, charge, and spin it has accumulated, with no memory of what the infalling matter used to be. Fact 77. If a particle of dark matter falls into a black hole, the black hole's mass increases by the dark matter particle's mass, but we have no way of knowing the black hole swallowed dark matter rather than ordinary matter. This highlights a deep point about black holes. They erase almost all information about what fell in dark matter, which makes up 85% of the matter in the universe, and which we've never directly detected because it doesn't emit, absorb, or reflect light, can nevertheless fall into black holes just like ordinary matter, because dark matter interacts gravitationally. In fact, black holes near the centers of galaxies, where dark matter density is high, probably accrete significant amounts of dark matter along with ordinary matter. The black hole grows, and from outside we can measure its mass increasing, but we can't tell how much of that mass came from ordinary matter and how much from dark matter. This could complicate efforts to measure black hole growth and compare it to theoretical models, because those models usually assume the accreted matter is ordinary baryonic matter, like hydrogen and helium. Fact 78. A black hole's entropy is enormous, much larger than the entropy of any normal object of comparable mass. This has profound implications for thermodynamics and the arrow of time. The second law of thermodynamics states that entropy always increases in isolated systems, driving the universe toward higher disorder and eventual heat death. Black holes having such high entropy represent the endpoint of this process for gravitational systems. When matter collapses into a black hole, the entropy of the universe increases dramatically. In the far future, after all stars have burned out and all matter has either dispersed or fallen into black holes, the universe will be dominated by black holes. Eventually, even the black holes will evaporate via Hawking radiation, leaving behind a dilute sea of particles. This final state has the maximum entropy possible, a completely disordered equilibrium state where no further change can occur. This is the ultimate fate of the universe according to thermodynamics, and black holes play a central role in this cosmic story. Fact 79. The ergosphere of a rotating black hole is a region where it's impossible to remain stationary, but it's still possible to escape. The boundary of the ergosphere, called the ergosurface or static limit, is located outside the event horizon. For a non-rotating black hole, the ergosurface coincides with the event horizon, so there's no ergosphere. But for a rotating black hole, the ergosurface is farther out, touching the event horizon at the poles but bulging out at the equator. Inside the ergosphere, space-time is dragged around by the black hole's rotation so strongly that any object, even one firing its rockets at full power in the opposite direction, must rotate with the black hole. You can't stand still, but you can still escape by firing your rockets and heading outward, eventually crossing the ergosurface and reaching a region where you can stop rotating. The ergosphere is where the Penrose process operates, allowing energy extraction from the black hole's rotation. It's also where the Blandford-Zonagek mechanism operates, using magnetic fields to tap into the black hole's rotational energy to power jets. Fact 80. Black holes can be used as natural laboratories to test general relativity in extreme conditions. Near a black hole, gravity is so strong that space-time curvature is enormous, much more than anywhere else in the accessible universe. Observing matter and light in these extreme conditions allows us to test whether general relativity correctly predicts what happens. So far, every test has confirmed Einstein's theory. The orbits of stars around Sagittarius A star match general relativity's predictions precisely. Gravitational waves from merging black holes have the exact form predicted by general relativity. The images from the Event Horizon Telescope match simulations based on general relativity. These tests probe gravity in regimes where the field is billions or trillions of times stronger than Earth's gravity, and still general relativity works perfectly. This doesn't mean general relativity is the final theory. We know it must be modified at the quantum level to incorporate quantum mechanics, but it tells us that general relativity is extraordinarily accurate in describing classical gravitational phenomena, even in the most extreme environments in the universe. Fact 81. Some theoretical physicists have speculated that our entire universe might exist inside a black hole. The idea is that the Big Bang, the beginning of our universe, might actually be the singularity inside a black hole that exists in a parent universe. From the inside, the singularity would appear as an initial moment of expansion, which is what we observe as the Big Bang. From the outside, in the parent universe, it would just be a black hole like any other. This idea, sometimes called the Schwarzschild cosmology, is highly speculative and not widely accepted, but it's an interesting thought experiment. If true, it would mean that every black hole in our universe could contain a new universe inside it, and our universe is nested inside a black hole in another universe, which itself might be inside another black hole, and so on, an infinite nesting of universes inside black holes. There's no way to test this idea with current technology, and it raises more questions than it answers, but it illustrates how black holes connect to the deepest questions about the nature and origin of the cosmos. Fact 82. The singularity at the center of a black hole is not a place in space but a moment in time. This is one of the most counterintuitive aspects of black hole geometry. Inside the event horizon, the roles of space and time switch. Outside the horizon, you can move freely in space but are forced to move forward in time. Inside the horizon, you can't avoid moving toward the singularity, just as you can't avoid moving forward in time when you're outside. The singularity is in your future, not in your spatial direction. No matter which direction you point, toward what used to be up, down, left, right, forward, backward, all paths lead to the singularity. It's unavoidable, not because there's a force pulling you, but because the geometry of space-time inside the horizon is such that all future directed paths end at the singularity. Physicist Kip Thorne described it as being like trying to avoid next Thursday. Just as you can't avoid next Thursday by moving in space, you can't avoid the singularity by moving in space once you're inside the event horizon. This is a profound statement about the nature of space-time and how it behaves in extreme gravitational fields. Fact 83. Hawking radiation creates entangled pairs of particles, with one particle escaping and the other falling into the black hole. This entanglement is at the heart of the information paradox. In quantum mechanics, entangled particles share a quantum state such that measuring one particle instantly affects the state of the other, regardless of the distance between them. When a particle escapes as Hawking radiation and its partner falls into the black hole, they remain entangled, but as the black hole evaporates and more particles escape, a problem arises. The escaping particles are entangled with particles inside the black hole, but they're also entangled with each other because they all came from the same black hole. A particle can't be maximally entangled with two different particles at once without violating the monogamy of entanglement, a principle in quantum information theory. This creates a paradox. Either information is lost when the black hole evaporates, violating unitarity, or the entanglement structure is more complex than we thought, perhaps involving quantum corrections to the geometry near the horizon or something else entirely that we don't yet understand. Recent work on the island formula and quantum extremal surfaces has made progress on resolving this, suggesting that information is preserved through subtle quantum correlations, but the full picture is still being developed. Fact 84. The firewall paradox, proposed in 2012 by Almheri, Marolf, Polchinski and Sully, often called the AMPS firewall, is a thought experiment that challenges our understanding of black holes and quantum mechanics. The paradox arises from trying to preserve unitarity, the principle that information is conserved in quantum mechanics, while also preserving the equivalence principle, the principle that free-falling observers experience no local effects at the event horizon. If information must be released in the Hawking radiation to preserve unitarity, then the particles escaping must have complex entanglement relationships with previously emitted particles, breaking their entanglement with the infalling partners. This means the event horizon can't be a smooth, empty region of space-time. Instead, there must be highly energetic entangled particles at the horizon, forming a firewall that would incinerate anything trying to cross. This contradicts the equivalence principle, which says that crossing the event horizon should be uneventful for a free-falling observer, with no special local physics at the horizon. So we have a conflict. Either information is lost, or the equivalence principle is violated, or our understanding of quantum mechanics and space-time is incomplete. The firewall paradox has generated intense debate and research, and various resolutions have been proposed, but there's no consensus yet. It's one of the major open problems in theoretical physics. Fact 85. Black holes can be described using quantum field theory and curved spacetime, which treats quantum fields like the electromagnetic field or matter fields in the curved spacetime geometry of general relativity. This semi-classical approach, where gravity is classical but matter is quantum, is how Hawking derived Hawking radiation. Quantum fields near the event horizon of a black hole behave differently from quantum fields in flat spacetime. The vacuum state, the lowest energy state of the field, is different. What looks like a vacuum to an observer far from the black hole looks like a thermal bath of particles to an observer near the horizon, and vice versa. This is related to the Unruh effect, where an accelerating observer in flat spacetime sees a thermal bath of particles even though an inertial observer sees a vacuum. The acceleration experienced by an observer hovering near a black hole's event horizon is enormous, and the Unruh temperature they'd measure corresponds roughly to the Hawking temperature. These connections between acceleration, temperature, and quantum fields in curved spacetime are deep and beautiful, revealing unexpected links between gravity, thermodynamics, and quantum mechanics. Fact 86. Black holes can have magnetic fields, though the black hole itself, being a vacuum region of spacetime, doesn't generate the field. Instead, magnetic fields are carried by the plasma in the accretion disk and the surrounding environment. These fields can become twisted and amplified by the disk's rotation and by the frame-dragging effects of a spinning black hole. The magnetic fields play a crucial role in the accretion process, transporting angular momentum outward through the disk via the magnetorotational instability, allowing matter to spiral inward. They also collimate and accelerate the jets launched from the black hole's poles. Observations of polarized light from the accretion disk and jets provide information about the structure and strength of these magnetic fields. The Event Horizon Telescope collaboration has even produced polarized images of the black holes in M87 and Sagittarius A star, showing the magnetic field structure near the event horizon in unprecedented detail. These observations are helping us understand how magnetic fields interact with black holes and how they power jets and regulate accretion. Fact 87. The energy released when two black holes merge is almost entirely in the form of gravitational waves, not electromagnetic radiation. Unlike the merger of neutron stars, which produces light across the electromagnetic spectrum from radio waves to gamma rays, black hole mergers are essentially dark. The black holes themselves don't emit light. If they have accretion disks, those might produce some light as they're disrupted during the merger, but for isolated black holes in empty space, the merger is invisible to traditional telescopes. The only signal is the burst of gravitational waves. This is why gravitational wave detectors like LIGO and Virgo are so important. They allow us to observe events that are otherwise completely invisible. The energy released in gravitational waves during a black hole merger is staggering. The first detected event, GW150914, released about 3 solar masses worth of energy in a fraction of a second, a luminosity exceeding the combined light output of all the stars in the observable universe. Yet if you were watching that region of space with optical telescopes, you'd see nothing. No flash, no explosion, no visible sign that anything happened. Only the gravitational wave detectors saw it. Fact 88. The ring-down phase of a black hole merger, when the newly formed black hole settles down after the collision, provides information about the final black hole's mass and spin. After 2 black holes merge, the resulting black hole is initially distorted, aspherical, oscillating. It rings like a bell, emitting gravitational waves at specific frequencies called quasi-normal modes. These modes depend only on the black hole's mass and spin, not on how it formed. By analyzing the ring-down signal in gravitational wave data, scientists can measure the mass and spin of the final black hole and test whether it behaves as general relativity predicts. So far, all ring-down observations match general relativity's predictions. The frequencies and damping times of the quasi-normal modes are exactly what theory predicts for a Kerr black hole. This is another confirmation that black holes exist as general relativity describes them, not as some exotic alternative object. Fact 89. The mass gap is a mysterious phenomenon in black hole astrophysics. Observations show that stellar mass black holes typically have masses above about 5 solar masses, while neutron stars have masses below about 2.5 solar masses. There's a gap between about 2.5 and 5 solar masses where very few compact objects are found. This gap is puzzling because theory doesn't predict it. When a massive star's core collapses, it should be possible to form compact objects anywhere in this mass range depending on the exact properties of the core and the explosion. Yet observations suggest these intermediate mass objects are rare. Possible explanations include the dynamics of supernova explosions preferentially creating objects either above or below the gap, selection biases in how we detect compact objects, or something about the equation of state of ultra-dense matter that we don't understand. Recent discoveries, including gravitational wave events with components in the mass gap, are starting to fill in this range and challenge our understanding. One event, GW190814, detected a merger involving a compact object with about 2.6 solar masses right in the middle of the gap. Is it a very heavy neutron star or a very light black hole? We don't know for sure, but these discoveries are forcing us to reconsider whether the mass gap is real or an observational artifact. Fact 90. The no-escape theorem in black hole physics states that once you cross the event horizon, reaching the singularity is inevitable and happens in finite proper time. There's no way to avoid it by clever maneuvers, powerful rockets, or any other means. The space-time geometry inside the horizon is such that all future directed paths, all possible trajectories through space-time that don't involve traveling faster than light, end at the singularity. You might delay reaching it slightly by firing rockets, but you can't avoid it. This is fundamentally different from being in orbit around a planet or star, where firing rockets can change your trajectory and allow you to escape. Inside a black hole, escape isn't just difficult or impractical, it's geometrically impossible. The future literally points toward the singularity. This inevitability is one of the most absolute and unforgiving aspects of black hole physics. Fact 91. Black holes can form from the direct collapse of massive gas clouds without going through a stellar phase, a process that might have been common in the early universe. In normal star formation, gas clouds collapse and fragment, forming many smaller stars. But in certain conditions, if the gas cloud is massive enough, hot enough, and rotating slowly, it might collapse directly without fragmenting, forming a massive black hole without ever forming a star. These direct collapse black holes could have masses of 10,000 to a million solar masses right from the start, providing seeds for supermassive black holes without needing millions of years of accretion and mergers. This might help explain how supermassive black holes became so massive so early in cosmic history. Conditions favoring direct collapse might have existed in the first few 100 million years after the Big Bang, when the gas was pristine, composed only of hydrogen and helium, without heavier elements to cool the gas efficiently. Direct collapse is still theoretical and hasn't been directly observed, but it's a leading candidate for seeding supermassive black holes. Fact 92. Supermassive black holes grow through a combination of gas accretion and mergers with other black holes. When galaxies collide and merge, their central black holes eventually sink to the center of the merged galaxy and form a binary system. Over time, they emit gravitational waves, spiral together and merge, creating an even more massive black hole. This hierarchical growth, where small black holes merge to form larger ones, which then merge to form even larger ones, is thought to be how supermassive black holes reached their current masses. Computer simulations of galaxy formation and evolution include models of black hole growth, and they can reproduce the observed relationship between black hole mass and galaxy properties, supporting this picture. Observations of in the same galaxy are both accreting and glowing, provide snapshots of this process in action. Fact 93. The slingshot effect can occur when a star or another object has a close encounter with a binary black hole system. The object can gravitationally interact with the binary, extracting orbital energy and being flung away at high speed while the binary becomes more tightly bound. This process, called gravitational slingshot or the gravitational assist, is the same principle used by spacecraft to gain speed when passing planets. Near a binary black hole, the speeds involved can be enormous. Stars can be accelerated to thousands of kilometers per second, fast enough to escape the galaxy entirely. These hypervelocity stars have been observed ejecting from the centers of galaxies, possibly by interactions with supermassive black hole. The slingshot effect also helps binary black holes shrink their orbits, overcoming the final parsec problem, a stage in binary evolution where stellar interactions and gas drag become inefficient at removing angular momentum. Fact 94. Black holes can tidally disrupt stars that pass too close, an event called a tidal disruption event or TDE. When a star ventures within the tidal radius of a black hole, the gravitational pull on the near side of the star is much stronger than on the far side. This difference, the tidal force, can exceed the star's self-gravity, ripping the star apart. Half of the star's material is flung outward at high speed, escaping the system, while the other half is captured by the black hole and forms an accretion disk. As the captured material heats up and spirals inward, it emits a bright flare of light that can outshine the entire galaxy for weeks or months before fading. TDEs are rare, occurring perhaps once every 10,000 to 100,000 years per galaxy, but when they happen, they're spectacular. They allow astronomers to study otherwise dormant black holes that aren't normally accreting and to probe the strong gravitational field near the event horizon. Dozens of TDEs have been observed in recent years using optical, ultraviolet, and X-ray telescopes. Fact 95. The tidal radius, the distance at which a star is disrupted by a black hole, depends on both the black hole's mass and the star's properties. For a solar mass star approaching a black hole, the tidal radius is approximately given by the formula R tidal equals R star times the cube root of mbh divided by m star, where R star is the star's radius, mbh is the black hole's mass, and m star is the star's mass. For a supermassive black hole with 1 million solar masses, The tidal radius is about 100 solar radii, or about half an astronomical unit, well outside the event horizon. So the star is torn apart before it crosses the horizon, and we can observe the disruption. For a stellar mass black hole with 10 solar masses, the tidal radius is inside the event horizon. The star would cross the horizon intact and be torn apart inside, hidden from view. This is why TDEs are associated with supermassive black holes in galactic centers, not stellar mass black holes. Fact 96. Some stars can survive close encounters with black holes, grazing the tidal radius without being fully disrupted. These are called partial tidal disruption events. The star loses some of its outer layers to the black hole, but the core remains intact and continues on its orbit, though now stripped of much of its mass. If the star passes close again, more material can be stripped. Over multiple passes, the star could be slowly consumed by the black hole in a series of partial disruptions. These events are harder to observe than full disruptions because the flares are weaker and repeat on the star's orbital period, which could be years or decades. But they've been observed in a few cases, providing insights into the dynamics of stars in the intense gravitational environment near supermassive black holes. Fact 97. Black holes can act as cosmic particle accelerators, accelerating particles to energies far beyond what human-made accelerators like the Large Hadron Collider can achieve. In the jets from active galactic nuclei and in the accretion disk, magnetic fields and the black hole's gravity can accelerate protons, electrons, and heavier nuclei to energies of up to 10 to the 20 electron volts or more. These ultra-high energy cosmic rays are the most energetic particles in the universe. When they collide with gas or magnetic fields, they produce cascades of secondary particles including gamma rays, neutrinos, and other particles. Black holes, through their jets and accretion processes, might be the sources of the ultra-high energy cosmic rays that bombard Earth. Identifying the sources of these cosmic rays is an ongoing effort in astrophysics. Facilities like the Pierre Auger Observatory detect ultra-high energy cosmic rays, and by tracing their directions back, astronomers try to identify their sources. Some events seem to come from the directions of active galaxies with supermassive black holes, supporting the idea that black holes are cosmic accelerators. Fact 98. Neutrinos, nearly massless particles that interact very weakly with matter, can be produced in the environments around black holes. When ultra-high energy protons in jets or accretion disks collide with photons or other particles, they can produce pions, which then decay into muons and neutrinos. Detecting these neutrinos from black hole systems would provide direct evidence of particle acceleration, and would allow us to study the processes happening near black holes in a way that's impossible with light alone, because neutrinos can escape from regions so dense that light is absorbed. The IceCube Neutrino Observatory at the South Pole detects high-energy neutrinos from space. In 2017, IceCube detected a high-energy neutrino that was traced back to a flaring blazar, a type of active galaxy with a jet pointing toward Earth powered by a supermassive black hole. This was the first time a neutrino was definitively associated with a specific astrophysical source beyond the Sun and a nearby supernova. It confirmed that blazars and their black holes are neutrino sources, opening a new window on black hole physics through multi-messenger astronomy combining light, gravitational waves, and neutrinos. Fact 99. Black holes in binary systems with companion stars can be X-ray binaries, where the black hole accretes matter from the companion star and emits X-rays. These systems come in two main types: low-mass X-ray binaries, where the companion is a low-mass star like a red dwarf or white dwarf, and high-mass X-ray binaries, where the companion is a massive star. The accretion process and X-ray emission allow us to detect and study black holes that would otherwise be invisible. By observing the orbital motion of the companion star and the X-ray variability, astronomers can measure the black hole's mass and study the accretion physics. Cygnus X1, the first widely accepted black hole candidate, is a high-mass X-ray binary, V404 Cygni, and GRS 1915 plus 105 are low-mass X-ray binaries, with some of the most massive stellar black holes known. These systems have provided much of our knowledge about stellar mass black holes. Fact 100. Some X-ray binaries show quasi-periodic oscillations with frequencies that provide information about the innermost regions of the accretion disk close to the event horizon. These high-frequency QPOs, with frequencies of tens to hundreds of hertz, are thought to arise from orbital motion near the ISCO or from oscillations in the disk structure. By measuring the QPO frequencies and how they vary with X-ray intensity, astronomers can estimate the black hole's mass and spin. Different models predict different relationships between QPO frequency and black hole parameters, so comparing observations with models helps us understand the accretion physics and test general relativity in the strong field regime. Fact 101. Black holes emit no light themselves, but they can appear bright due to the light emitted by the hot accretion disk and jets. The amount of light emitted depends on the accretion rate. A black hole that's not accreting, isolated in empty space, is completely dark and invisible except for its gravitational effects. A black hole accreting at a modest rate might be a faint X-ray source. A black hole accreting near the Eddington limit is incredibly bright, potentially outshining an entire galaxy. This range from invisible to ultraluminous means black holes can be in many different observational states, and detecting them requires different techniques depending on whether they're active or quiescent. Fact 102. The metallicity of a star, the abundance of elements heavier than helium, affects whether its core will form a black hole and how massive that black hole will be. Stars with low metallicity have weaker stellar winds because metals in the star's atmosphere drive the winds through radiation pressure. With weaker winds, the star retains more mass throughout its life, leading to a more massive core and potentially a more massive black hole. This is why astronomers think the first stars in the universe, which formed from pristine gas with essentially zero metallicity, might have produced more massive black holes than stars formed today. It might also explain why gravitational wave detections have found black holes more massive than expected from large stellar populations. Fact 103. Intermediate mass black holes might form in dense star clusters through runaway collisions. In a dense cluster, stars collide and merge, forming one massive star. If this process runs away, the most massive star in the cluster colliding repeatedly with other stars, it can grow to hundreds or even 1,000 solar masses. When such a massive star dies, it could form an intermediate mass black hole. This process is most efficient in young dense clusters where stars are packed closely together and moving at high speeds. Globular clusters, which are old and dense, might harbor intermediate mass black holes formed this way early in the cluster's history. Detecting these black holes is challenging because they don't accrete much matter in the sparse environment of a globular cluster, but their gravitational effects on nearby stars can reveal their presence. Fact 104. Black holes can be detected through microlensing, where the black hole passes in front of a distant star and its gravity bends the star's light, causing the star to brighten temporarily. The duration and shape of the brightness curve depend on the black hole's mass, distance, and velocity. Microlensing surveys that monitor millions of stars in the galactic bulge or in nearby galaxies have detected several black hole candidates this way. One advantage of microlensing is that it can detect isolated black holes that have no companion star and no accretion disk, black holes that would otherwise be completely invisible. This technique is helping us understand the population of stellar mass black holes in the galaxy. Fact 105. The galactic center of the Milky Way is one of the best places to study black holes because Sagittarius, a star, is so close, relatively speaking, and because the environment is rich with stars and gas. Observations of stars orbiting Sagittarius, a star, have been conducted for over 20 years using large telescopes like the Keck Observatory in Hawaii and the Very Large Telescope in Chile. By tracking the orbits of these stars with extreme precision, astronomers have measured the black hole's mass to be about 4.1 million solar masses with an uncertainty of only a few percent. One star, Set 2, has a highly elliptical orbit that brings it within 17 light-hours of the black hole at closest approach, moving at nearly 2% of the speed of light. At that distance and speed, relativistic effects are measurable. Astronomers have detected the gravitational redshift of starlight as S2 climbs out of the black hole's gravitational well, and the precession of the orbit due to general relativity. These observations provide some of the strongest tests of general relativity in a strong gravitational field. Fact 106. The discovery of gravitational waves has opened up a completely new way to observe the universe, and black holes have been the primary sources detected so far. Before LIGO's first detection in 2015, gravitational waves were theoretical predictions that had never been directly observed. Now we've detected dozens of events, mostly black hole mergers but also neutron-star mergers, and possible neutron-star-black hole mergers. Each detection provides information about the masses, spins, and distances of the merging objects, allowing us to study black hole populations statistically. We're learning how common black hole mergers are, how black holes form and evolve, and whether their properties match theoretical predictions. Gravitational wave astronomy is still young, but it's already revolutionized our understanding of black holes and opened up entirely new areas of research. Fact 107. Third-generation gravitational wave detectors currently being planned will be far more sensitive than current detectors and will observe black hole mergers across the entire universe. The Einstein Telescope in Europe and Cosmic Explorer in the United States are planned facilities that will have arms tens of kilometers long, and sensitivity improved by a factor of 10 or more. Compared to LIGO, they'll detect black hole mergers out to redshifts of 20 or more, seeing the first black holes that formed in the universe, and they'll measure the properties of mergers with exquisite precision, testing general relativity in ways that are currently impossible. These next-generation detectors will also detect thousands of events per year, providing a huge statistical sample for population studies. Fact 108. Space-based gravitational wave detectors like LISA, the Laser Interferometer Space Antenna, will observe low-frequency gravitational waves from supermassive black hole mergers, compact object inspirals into supermassive black holes, and potentially from exotic sources like cosmic strings. LISA will consist of 3 spacecraft in a triangular formation separated by 2.5 million kilometers, following Earth in its orbit around the Sun. Laser beams will travel between the spacecraft, and gravitational waves passing through will change the distances slightly, which the detectors will measure. LISA will be sensitive to frequencies from millihertz down to tens of microhertz, much lower than LIGO's frequency range, allowing it to observe sources that LIGO can't detect. Supermassive black hole mergers, which emit gravitational waves at low frequencies due to their enormous masses, will be prime targets for LISA. The mission is currently in development with a planned launch in the 2030s. Fact 109. Pulsar timing arrays are another method for detecting gravitational waves, using millisecond pulsars as cosmic clocks. Gravitational waves passing through the galaxy stretch and squeeze space-time, causing tiny variations in the arrival times of pulsar signals at Earth. By monitoring many pulsars across the sky and looking for correlated timing variations, astronomers can detect gravitational waves with periods of years corresponding to frequencies of nanohertz. These ultra-low frequency gravitational waves are produced by supermassive black hole binaries with masses of hundreds of millions to billions of solar masses orbiting each other over decades or centuries before merging. Several pulsar timing array projects around the world, including NINAGRAV in North America, the European Pulsar Timing Array and the Parkes Pulsar Timing Array in Australia, are collaborating to detect these signals. In 2023, these collaborations announced evidence of a gravitational wave background, a stochastic signal possibly from countless supermassive black hole binaries across the universe, though confirmation is ongoing. Fact 110. Black holes are predicted to exist in a wide range of masses from the Planck mass, about 22 micrograms, up to the largest supermassive black holes of tens of billions of solar masses, a range spanning more than 40 orders of magnitude. This enormous range reflects the diverse ways black holes can form and grow. The universe is remarkably good at creating black holes across this entire spectrum. The smallest, if they exist, would be primordial black holes from the early universe. The largest grow over billions of years through accretion and mergers, and everything in between. Stellar mass black holes from collapsing stars, intermediate mass from stellar collisions or direct collapse, demonstrates that black holes are a fundamental feature of the universe's structure. Fact 111. The existence of black holes was doubted by many physicists for decades after Einstein published general relativity, even though the mathematics allowed them. Einstein himself didn't believe they were real. Eddington, another prominent physicist, thought nature would find a way to prevent their formation. It wasn't until observational evidence accumulated in the 1960s and 70s, particularly the discovery of Cygnus X1 and quasars, that the scientific community began to accept that black holes actually exist in nature. The full acceptance took even longer. Today, black holes are considered proven objects, with overwhelming evidence from X-ray binaries, galactic centers, gravitational waves, and direct imaging. It's a reminder that theoretical predictions, no matter how solid the mathematics, require observational confirmation. Fact 112. The term singularity in black hole physics refers to a place where physical quantities like density and curvature become infinite, indicating a breakdown of the theory. General relativity predicts singularities at the centers of black holes, but most physicists believe this prediction signals that general relativity is incomplete. Just as Newtonian mechanics breaks down at high speeds and is replaced by relativity, general relativity likely breaks down at the singularity and must be replaced by a quantum theory of gravity. What actually exists at the center of a black hole, replacing the classical singularity, is one of the biggest unsolved problems in physics. Candidates include quantum fluctuations preventing infinite density, space-time foam at the Planck scale, bounces leading to new universes, or structures from string theory like fuzzballs. Until we have experimental tests of quantum gravity, we won't know for sure. Fact 113. The connection between black holes and thermodynamics is one of the most profound discoveries in theoretical physics. Black holes have temperature, entropy, and energy, and they obey laws that are mathematically identical to the laws of thermodynamics. The first law relates changes in a black hole's mass to changes in area, charge, and angular momentum, analogous to the first law of thermodynamics relating energy, temperature, and entropy. The second law states that black hole area never decreases, analogous to entropy, never decreasing. The third law states that you can't reduce a black hole's temperature to absolute zero in a finite number of steps, analogous to the third law of thermodynamics. This parallel suggests a deep connection between gravity, information, and thermodynamics that we're still working to fully understand. Black hole thermodynamics has inspired holography, quantum information approaches to spacetime, and new ways of thinking about what gravity actually is. Fact 114. Black holes can be considered the ultimate information storage devices. The Bekenstein bound, derived from black hole thermodynamics, states that the maximum amount of information that can be stored in a given region of space is proportional to the area of the region's boundary, not its volume. For a spherical region of radius r, the maximum entropy is roughly S equals 2 pi k r squared divided by the Planck area. This bound applies to any physical system, not just black holes, and it represents a fundamental limit on information density. Black holes saturate this bound, meaning they store the maximum possible information for their size. This has implications for information theory, computer science, and the nature of physical law. It suggests that the universe has a maximum information density and that physics at the deepest level might be about information rather than matter or energy. Fact 115. The Planck scale, defined by fundamental constants of nature, sets the scale where quantum gravity effects become important. The Planck length is about 1.6 times 10 to the negative 35 meters. The Planck time is about 5.4 times 10 to the negative 44 seconds, and the Planck mass is about 22 micrograms. At scales approaching the Planck length, space-time itself becomes uncertain, fluctuating quantum mechanically. Black holes with masses near the Planck mass, if they existed, would have event horizons about 1 Planck length in size. At these scales, classical general relativity breaks down completely, and quantum gravity dominates. Understanding physics at the Planck scale is necessary for understanding the true nature of black hole singularities, the very early universe, and the fundamental structure of space-time. It's one of the ultimate goals of theoretical physics, and black holes are intimately connected to this quest. Fact 116. Black holes could theoretically be used for interstellar travel through gravitational assists. A spacecraft could approach a black hole, swing around it in a carefully calculated trajectory, and be flung away at much higher speed than it arrived, having extracted energy from the black hole's rotation or orbit. This is an extension of the gravitational slingshot technique used by spacecraft in our solar system, but the extreme gravity of a black hole allows for much greater velocity changes. A civilization with advanced technology could potentially use black holes as waypoints in a network of gravitational assist trajectories spanning the galaxy, enabling travel at relativistic speeds. Of course, the challenges would be enormous, requiring precise navigation, protection from radiation and tidal forces, and the ability to control the spacecraft's trajectory in intense gravitational fields. But theoretically, it's possible. Fact 117. If you could survive near a black hole, you could use the time dilation to send messages to the far future. By orbiting close to the event horizon where time passes slowly, you could wait a short time by your clock while centuries or millennia pass in the outside universe. Then you could send a radio signal or light beam outward, and it would arrive in the distant future. This is a form of one-way communication with future civilizations. You couldn't receive replies because by the time the reply was sent, you'd have experienced only a short time and wouldn't be waiting anymore. Or you'd need to continue orbiting to receive signals from even further in the future. But as a way to send information or warnings to the future, it could work. This is pure speculation, of course, but it illustrates the strange possibilities that relativity allows. Fact 118. Black holes might be the key to understanding dark energy, the mysterious force causing the universe's expansion to accelerate. Some theoretical ideas link dark energy to properties of space-time on quantum scales, and black holes, being regions where space-time is most extreme, might hold clues. One speculative idea is that black holes contribute to dark energy through their quantum evaporation, with the accumulated energy of all evaporating black holes across the universe acting like a cosmological constant. Another idea involves holographic principles, where the universe's dark energy is related to information on a cosmological horizon. These ideas are highly speculative and far from proven, but they show how black holes connect to the biggest mysteries in cosmology. Fact 119. The image of a black hole from the Event Horizon Telescope is not a photograph in the traditional sense. It's a reconstructed image created from radio interferometry data using sophisticated algorithms. The data consists of correlations between signals received at different telescopes separated by thousands of kilometers. From this data, which is sparse and noisy, computer algorithms reconstruct what the radio emission from the black hole environment must look like to produce those correlations. Multiple algorithms developed independently by different teams were used to ensure the reconstruction was reliable. The algorithms produced consistent images, giving confidence that the final image is accurate. This process, called interferometric imaging, is an amazing combination of physics, mathematics, and computer science, pushing the limits of what's possible with current technology. Fact: 120 black holes could hypothetically be used as extremely efficient power sources if we could harness the Penrose process or the Blandford-Zinajek mechanism. These processes extract rotational energy from a spinning black hole, converting it to usable energy with efficiencies up to 29% for the Penrose process and even higher for the Blandford-Zinajek process with strong magnetic fields. Compare this to nuclear fusion, which converts about 0.7% of mass to energy, or nuclear fission at about 0.1%. Black hole energy extraction is theoretically far more efficient than any other process. A sufficiently advanced civilization could build structures around a rotating black hole to capture energy from jets or to use magnetic fields to siphon off rotational energy. This is the basis for black hole power plants in some science fiction, and while it's speculative and far beyond our current technology, it's not prohibited by physics. Fact: 121 some supermassive black holes are recoiling, moving through their host galaxies at speeds of thousands of kilometers per second, kicked by the gravitational waves emitted during an asymmetric merger. When two black holes merge, if their masses and spins are misaligned, the gravitational waves are emitted preferentially in certain directions, creating a net momentum. By conservation of momentum, the merged black hole recoils in the opposite direction. If the kick velocity exceeds the galaxy's escape velocity, the black hole can be ejected entirely, becoming a wandering black hole in intergalactic space. Several candidate recoiling black holes have been observed, identified by their offset positions from galactic centers or by Doppler shifts in emission lines indicating high velocities. These recoiling black holes are rare but important for understanding black hole merger dynamics in galactic evolution. Fact: 122 black holes can store angular momentum, and the maximum amount they can store is determined by the Kerr bound, where the spin parameter a equals 1. At this maximum spin, the black hole is rotating at the speed of light at its equator. If you tried to add more angular momentum by dropping in rotating material, the black hole would either radiate the excess away through gravitational waves and superradiance, or the properties of the accretion disk would change to prevent further spin-up. The cosmic censorship hypothesis suggests that nature always prevents black holes from exceeding this limit, ensuring the singularity remains hidden. Observations of black hole spins, measured through X-ray spectroscopy and other techniques, find values ranging from near zero to close to the maximum, indicating that black holes in nature span the full range of possible spins. Fact: 123 superradiance is a quantum mechanical and classical phenomenon where waves can extract energy from a rotating black hole. When a wave such as an electromagnetic wave or a gravitational wave with appropriate frequency and angular momentum scatters off a rotating black hole's ergosphere, it can be amplified, emerging with more energy than it came in with. The extra energy comes from the black hole's rotational energy. This process could theoretically be used to extract energy from black holes, a variation on the Penrose process. Superradiance also has implications for the stability of rotating black holes and for the formation of clouds of ultralight particles around black holes, which could be detected through their gravitational wave signals. Fact: 124. Black hole bombs are hypothetical systems where superradiance is enhanced by placing a mirror around a black hole, causing the amplified waves to bounce back and extract more energy in a runaway process. If the mirror reflects waves efficiently, the energy extraction accelerates exponentially, potentially leading to an explosion or to the complete spin-down of the black hole. While artificial mirrors are science fiction, nature could create something similar if ultralight particles like axions exist. These particles could form bound states around spinning black holes, extracting angular momentum through superradiance and forming an axion cloud. The cloud's presence would affect the black hole's gravitational wave signal and could provide a way to detect axions, particles that are candidates for dark matter. This is an area of active research connecting particle physics, black holes, and dark matter. Fact 125. The relativistic jets from black holes can extend for millions of light years, far larger than the black hole itself or even the host galaxy. The jet from the galaxy M87, for instance, extends for about 5,000 light years, visible in optical and radio images. Other jets extend even farther into intergalactic space, creating huge lobes of radio-emitting plasma. These jets are among the largest structures created by single objects in the universe. The energy required to maintain them is staggering, often equivalent to the rest mass energy of millions or billions of stars, yet they're powered by accretion onto a black hole with a tiny event horizon, perhaps only a few times the size of our solar system. This is a testament to the efficiency of black holes in converting gravitational energy into kinetic energy and radiation. Fact 126. The connection between black holes and galaxy evolution is now well established. Supermassive black holes regulate star formation in their host galaxies through feedback. When the black hole is actively accreting, the energy it releases heats the surrounding gas, preventing it from cooling and collapsing to form stars. This quenches star formation. When the black hole is quiescent, gas can cool and form stars again. This cycle of feedback and star formation has shaped the properties of galaxies over cosmic time. The tight correlations between black hole mass and galaxy properties, like the M-sigma relation, are evidence of this coevolution. Understanding how black holes and galaxies grow together is a major area of research in astrophysics. Fact 127. Black holes can produce echoes in their gravitational wave signals if exotic physics modifies the spacetime near the event horizon. According to general relativity, once a black hole forms and settles down, it rings briefly and then becomes silent. But if there's structure near the horizon, perhaps from quantum effects or from the black hole not having a true event horizon, but instead a surface slightly outside, gravitational waves could reflect off this structure and produce echoes, repeated signals arriving shortly after the main merger signal. Searching for echoes in gravitational wave data is ongoing. Some studies have claimed tentative detections, but the signals are at the edge of detectability and could be noise. If confirmed, echoes would indicate new physics beyond general relativity, possibly evidence of quantum gravity effects. So far, most analyses find no convincing evidence for echoes, supporting the idea that black holes behave as general relativity predicts. Fact 128. The shadow of a black hole, the dark region seen in Event Horizon Telescope images, is actually larger than the event horizon itself. For a non-rotating Schwarzschild black hole, the shadow has a radius of about 2.6 times the Schwarzschild radius, or 5.2 times gm divided by c squared. This is because photons traveling near the black hole are bent by gravity, and the edge of the shadow corresponds roughly to photons orbiting at the photon sphere before being captured or escaping. For a spinning Kerr black hole, the shadow is distorted, slightly smaller on the side rotating toward the observer, and larger on the side rotating away, creating an asymmetry. Measuring the shadow's size and shape allows astronomers to determine the black hole's mass and spin, and to test general relativity. Fact 129. Black holes are the most gravitationally bound objects in the universe. meaning it requires more energy to disassemble a black hole than any other object of comparable mass. Specifically, the binding energy of a black hole, the energy required to disperse its mass to infinity, is equal to the black hole's rest mass energy, E equals mech squared, minus the energy that could be extracted through processes like the Penrose process or Hawking radiation. For a non-rotating black hole, the binding energy is essentially the full rest mass energy. For a maximally rotating black hole, up to 29% of the rest mass energy can be extracted through the Penrose process, so the binding energy is about 71% of the rest mass. Either way, black holes are incredibly tightly bound, more so than atomic nuclei where binding energies are less than 1% of the rest mass, and vastly more than stars or planets where gravitational binding energies are tiny fractions of the rest mass. Fact 130. The formation of a black hole from a collapsing star is one of the fastest and most violent events in the universe. From the moment nuclear fusion stops in the core to the formation of the event horizon takes less than a second. The core collapses from roughly the size of Earth to a point in about a quarter of a second. The rebound and supernova explosion happen within seconds. The energy released in neutrinos during the core collapse is about 10 to the 46 joules, 100 times more than the energy released in light and kinetic energy in the supernova. For a brief moment, the collapsing core is the brightest source of neutrinos in the universe, outshining all other sources combined. This neutrino burst was detected from supernova 1987A in the Large Magellanic Cloud, a galaxy near the Milky Way, confirming our understanding of core collapse. Fact 131. The future of the universe in the far distant future, trillions of years from now, will be dominated by black holes. Stars will have burned out. Galaxies will have dispersed or merged. The expansion of the universe will have carried distant structures beyond our observable horizon. What remains will be black holes, planets, asteroids, and cold remnants drifting through an ever-expanding, ever-darkening cosmos. Eventually, even the black holes will evaporate via Hawking radiation, though this will take unimaginably long. A solar mass black hole takes about 10 to the 67 years to evaporate. A supermassive black hole with a billion solar masses takes about 10 to the 96 years. After the last black hole evaporates, the universe will contain only a dilute sea of particles and radiation, spread thinner and thinner by expansion, approaching the state of maximum entropy and minimum temperature, a fraction of a degree above absolute zero. This is the heat death or big freeze scenario for the universe's fate. It's a bleak picture, but it's what thermodynamics and cosmology predict. Fact 132. Some physicists have speculated that black holes could be conscious or could process information in ways analogous to computation. The holographic principle suggests that information is stored on the event horizon, and some have proposed that the dynamics of this information could be interpreted as a form of computation. The timescales would be bizarre, with Planck time updates happening at the horizon, but the total information capacity is enormous. A supermassive black hole could theoretically store and process more information than any computer we could ever build. Whether this constitutes consciousness or intelligence in any meaningful sense is highly speculative and philosophical. Most physicists are skeptical, but it's an interesting thought experiment about the nature of information and consciousness. Fact 133. Black holes are the ultimate test of our physical theories because they combine extreme gravity, quantum mechanics, thermodynamics, and information theory in ways that push every theory to its limits. General relativity predicts singularities where it breaks down. Quantum mechanics predicts information loss that violates unitarity. Thermodynamics predicts entropy proportional to area instead of volume. Information theory faces paradoxes about where information goes. Reconciling all these aspects requires a theory of quantum gravity that we don't yet have. Black holes are where the next revolution in physics will happen. Just as black body radiation and atomic spectra led to quantum mechanics a century ago, understanding black holes fully will likely require new concepts in mathematics that we can barely imagine today. Fact 134. The role of black holes in the formation of heavy elements is an area of active research. When neutron stars merge, they produce R-process elements, heavy elements like gold and platinum, through rapid neutron capture. Black holes might also play a role, either through material ejected during black hole-neutron star mergers, or through jets that process material at extreme energies and temperatures. Some of the gold in your jewelry, the iodine in your body, the rare earth elements in your smartphone, might have been forged in events involving black holes. Every element heavier than iron in your body was created in stellar explosions or compact object mergers, and black holes are part of the story of cosmic nucleosynthesis. Fact 135. Black holes can exist in stable orbits around each other for billions of years before merging, creating binary systems that persist for a significant fraction of the age of the universe. Two supermassive black holes from merged galaxies might orbit each other at a separation of light years or hundreds of light years, taking millions or even billions of years to spiral together through gravitational wave emission. During this time, they influence their environment, scattering nearby stars, accreting gas and shaping the dynamics of the galactic center. These long-lived binaries are targets for pulsar timing arrays and future space-based gravitational wave detectors. Fact 136. The chirp signal of a gravitational wave from merging black holes, where the frequency and amplitude increase rapidly as the objects spiral together, is one of the most distinctive signatures in astrophysics. The chirp encodes information about the masses and spins of the merging objects. By analyzing the chirp, scientists can measure the parameters of the system. The term chirp is used because if you converted the gravitational wave signal to sound, it would sound like a rising pitch, like a bird's chirp. LIGO scientists have done exactly this, creating audio files of gravitational wave events by shifting the frequencies into the audible range. Listening to these chirps is eerie and profound, hearing the sound of space-time itself vibrating as black holes collide billions of light years away. Fact 137. Black holes can be used to test the equivalence principle, one of the cornerstones of general relativity, which states that gravitational and inertial mass are equivalent, and that locally, gravitational fields are indistinguishable from acceleration. By observing how light and matter behave near black holes where gravity is extreme, we can test whether the equivalence principle holds. So far, all observations confirm it. Stars orbiting Sagittarius, a star, move on trajectories consistent with the equivalence principle. Gravitational waves from merging black holes propagate as the equivalence principle predicts. Light bending near black holes matches predictions. These tests in strong field regimes give us confidence that the equivalence principle is a fundamental aspect of nature. Fact 138. The study of black holes is inherently interdisciplinary, combining general relativity, quantum mechanics, thermodynamics, astrophysics, cosmology, information theory, and even philosophy. To fully understand black holes requires knowledge from all these fields and the ability to see connections between them. This makes black hole research intellectually rich and challenging. It also means that progress in understanding black holes often comes from unexpected directions, from insights borrowed from one field applied to another. The holographic principle came from string theory. Hawking radiation came from quantum field theory applied to curved spacetime. The M-sigma relation came from observational astronomy. Black holes are a nexus where many areas of physics meet. Fact 139. Observing black holes has required developing new technologies and techniques. from X-ray telescopes in space to radio interferometry networks spanning continents to gravitational wave detectors with sensitivity at the limits of engineering. Each new technology has revealed new aspects of black holes. X-ray telescopes discovered X-ray binaries. Very long baseline interferometry allowed the Event Horizon Telescope to image black holes. Gravitational wave detectors opened an entirely new observational window. Future technologies like space-based detectors and next-generation radio arrays will reveal even more. The history of black hole research is intertwined with the history of observational technology. Fact 140. Black holes challenge our intuitions about space and time because they exist in regimes where everyday experience is completely irrelevant. We evolved on a planet with weak gravity and slow speeds, where Newtonian physics is an excellent approximation. Black holes are nothing like that environment. Near a black hole, space and time swap roles. Escape becomes impossible, not because of a force, but because of geometry. Time runs at different rates depending on where you are. Simultaneity is ambiguous. Our intuitions, honed by millions of years of evolution in a Newtonian environment, are worse than useless near black holes. We have to rely on mathematics and the logical structures of physical theories, not on intuition, to understand them. Fact 141. The mathematics describing black holes, differential geometry and tensor calculus, is beautiful and elegant. Einstein's field equations, which describe how space-time curves in response to mass and energy, are written as 10-coupled nonlinear partial differential equations. Solutions to these equations, like the Schwarzschild and Kerr solutions, have a simplicity and symmetry that physicists find aesthetically pleasing. The fact that such complex phenomena emerge from such relatively simple equations is one of the wonders of theoretical physics. Roger Penrose once said that the Kerr solution, describing a rotating black hole, was so elegant that it must be telling us something deep about the universe. The mathematical beauty of black hole solutions has inspired generations of physicists and mathematicians. Fact 142. Black holes have inspired philosophical questions about the nature of reality, time, causality, and existence. If information is lost in black holes, what does that mean for determinism and predictability? If singularities exist where physical laws break down, what does that say about the limits of science? If the interior of a black hole is cut off from our universe, does it still exist in a meaningful sense? These questions venture beyond physics into metaphysics, but they're motivated by physical theories and observations. Black holes force us to confront deep questions about what we mean by existence, reality, and knowledge. Fact 143. The cultural impact of black holes extends beyond science. They've captured the public imagination, appearing in countless science fiction stories, movies, TV shows, and popular culture. From the film Interstellar, which worked with physicist Kip Thorne to create scientifically accurate depictions of black holes and their effects, to the term black hole being used metaphorically to describe anything that consumes resources without giving anything back, black holes have become cultural icons. They symbolize the mysterious, the powerful, the unknown. They've inspired art, music, literature, and philosophy. This cultural resonance reflects something deep about human curiosity and our fascination with the extreme and the unknowable. Fact 144. The discovery of black holes is one of humanity's great intellectual achievements, comparable to the discovery of DNA's structure, the development of quantum mechanics, or the realization that Earth orbits the Sun. We've gone from theoretical speculation in the early 20th century to direct detection in the early 21st century. We've confirmed that these bizarre predictions of general relativity actually exist in nature. We've observed them in multiple ways: through X-rays, through gravitational effects on stars, through gravitational waves, through direct imaging. We've measured their properties, studied their behavior, and used them to test fundamental physics. Future generations will look back on this era as the time when black holes transitioned from theoretical curiosities to observed, understood objects. Fact 145. There are likely black holes passing through the Milky Way right now that formed in other galaxies and were ejected or wandered into intergalactic space. These nomadic or rogue black holes would be incredibly difficult to detect unless they happen to accrete gas or pass in front of a star, causing a microlensing event. The Milky Way has probably captured some of these wanderers over its history, adding to the population of black holes in our galaxy. Some might be lurking in the halo or disk, invisible and unsuspected. The universe could be full of wandering black holes between galaxies, the remnants of violent mergers and ejections over cosmic history. Fact 146. Black holes are among the longest-lived objects that will exist in the universe. While stars burn out in millions to trillions of years, and even protons might decay after 10 to the 35 years or more in some theories, black holes can persist for 10 to the 67 to 10 to the 100 years or longer, depending on their mass. A supermassive black hole formed in the early universe will outlive nearly everything else by incomprehensible timescales. In the far future, when the universe is cold and dark, black holes will be the last macroscopic structures, slowly evaporating into the void. The universe's longest-term investment in structure. This correspondence has been used to study quantum chromodynamics, the theory of the strong nuclear force, and condensed matter physics, using calculations in gravity to understand quantum field theories. Black holes have become tools for understanding quark-gluon plasmas, superconductors, and other systems that seem completely unrelated to astrophysics. This is one of the most surprising and powerful insights to emerge from theoretical physics in recent decades. Fact 148. If you could somehow build a particle accelerator near a black hole's event horizon, you could achieve arbitrarily high collision energies in the center of mass frame by colliding particles that fall in from different directions. This is called the Penrose collision mechanism. Near the horizon, particles can have unbounded energies as measured by certain observers, and collisions can reach Planck scale energies or higher, potentially probing quantum gravity. This is purely theoretical, since building an accelerator near a black hole is impossible with any foreseeable technology, but it shows that black holes could serve as natural particle accelerators for probing the highest energy physics. Fact 149. The concept of a black hole has evolved over time as our understanding has deepened. Early concepts, like Michel's and Laplace's dark stars, imagined objects where escape velocity exceeded light speed but still thought of light as particles obeying Newtonian mechanics. Einstein's general relativity gave us a space-time description where black holes are regions of curved space-time. Quantum mechanics added Hawking radiation and thermodynamics. String theory adds fuzzballs and microstate counting. Each layer of understanding has changed what we mean by a black hole. Future theories will likely add more layers, further refining the concept. Black holes are not static ideas, they're evolving as our physics evolves. Fact 150. Black holes might be the key to a theory of everything. A unified theory combining all fundamental forces and explaining all particles and interactions. Quantum gravity, which would describe black holes at the most fundamental level, is deeply connected to string theory, M-theory, loop quantum gravity, and other candidate theories of everything. Understanding how gravity and quantum mechanics merge at black holes' singularities and horizons is one of the paths toward this unified understanding. Many physicists believe that whoever solves the black hole information paradox and fully understands quantum gravity will have taken a major step toward a theory of everything. Fact 151. The properties of black holes are independent of the history of how they formed, a consequence of the no-hair theorem. Whether a black hole formed from the collapse of a star, the merger of two smaller black holes, or the direct collapse of a gas cloud, if they end up with the same mass, charge, and spin, they're identical. This is remarkable because it means black holes are uniquely simple despite being formed through complex, chaotic processes. The final state depends only on three numbers. Everything else is forgotten. This simplicity is part of what makes black holes tractable mathematically and theoretically. Fact 152. Black holes can serve as laboratories for testing exotic theories. For example, theories of modified gravity that propose alternatives to general relativity can be tested by comparing their predictions for black hole properties and behavior to observations. If observations of black hole shadows, gravitational waves, or other phenomena don't match general relativity's predictions, it could indicate new physics. So far, general relativity passes all tests, but the search continues. Black holes are where the effects of modified theories would be most apparent, making them ideal testing grounds. Fact 153. The speed at which information can be transmitted near a black hole is limited by the speed of light, but observers at different locations perceive time differently due to time dilation. An observer hovering close to the event horizon experiences time much more slowly than an observer far away. If they tried to communicate, the signals would be severely redshifted and delayed. This creates strange communication scenarios where messages sent at regular intervals by one observer arrive at vastly different intervals to another observer. Managing communication near black holes would require accounting for these relativistic effects, which makes coordinated actions extremely difficult. Fact 154. Black holes can theoretically exist in any universe where general relativity or a similar theory of gravity applies. If there are parallel universes or a multiverse with different physical constants, those universes would have black holes if gravity is strong enough and objects can collapse. The properties of black holes in those universes might differ if constants like the speed of light or the gravitational constant have different values, but the fundamental concept of a region where gravity is so strong that nothing can escape would still apply. Black holes are a universal consequence of gravity. Fact 155. The evaporation of black holes via Hawking radiation suggests that black holes are not eternal, contradicting the classical view. Even the largest supermassive black holes will eventually evaporate, though it will take times vastly longer than the current age of the universe. This means the universe's future is finite in terms of the existence of black holes. Eventually, every black hole will disappear, leaving only radiation. This ties into the fate of the universe and the arrow of time, suggesting that the universe moves toward a state of maximum entropy where no structure remains. Fact 156. Black holes have an effective temperature and can be in thermal equilibrium with radiation, meaning they can absorb and emit energy at equal rates. For black holes much larger than the Planck mass, the Hawking temperature is far below the cosmic microwave background temperature, so they absorb more radiation than they emit and slowly grow. But in the far future, as the universe expands and cools, the CMB temperature will drop below the Hawking temperature of even supermassive black holes. At that point, they'll start evaporating, slowly shrinking over unimaginable timescales. Fact 157. The mathematics of black holes has inspired new mathematical techniques and concepts. Penrose diagrams, which represent the causal structure of space-time in a compact form, were developed to understand black holes. These diagrams have become standard tools in general relativity. Techniques for solving the Einstein field equations, perturbation theory, numerical relativity all have been advanced by the challenge of understanding black holes. The study of black holes has driven mathematical progress in differential geometry, topology, and computational methods. Fact 158. Black holes can exist in higher dimensional spaces proposed by string theory, and their properties are different. In 10 or 11 dimensions, black holes can have more complex horizon topologies and their thermodynamics differ. Studying these higher dimensional black holes helps physicists understand string theory and quantum gravity. Some features that seem paradoxical in 4 dimensions become clearer in higher dimensions, and vice versa. This interplay between different dimensional scenarios enriches our understanding. Fact 159. The observational confirmation of black holes took decades of work by thousands of scientists across multiple disciplines, from early X-ray astronomers who detected Cygnus X1, to radio astronomers who observed jets from AGN, to infrared astronomers who tracked stars orbiting Sagittarius A star, to gravitational wave physicists who built LIGO, to the Event Horizon Telescope team who imaged black hole shadows, each contribution built on previous work. Science is a collective human enterprise, and the story of black hole discovery is a testament to international collaboration, persistence, and ingenuity. Fact 160. Black holes are not just objects of academic interest. They have practical implications for understanding our universe's structure, evolution, and fate. They're connected to galaxy formation, star formation, the distribution of elements, the nature of space-time, and fundamental physics. Understanding black holes helps us understand where we came from, the processes that created the elements in our bodies, and the ultimate fate of everything. They're part of the cosmic story that includes us. Fact 161. The possibility of primordial black holes existing as dark matter is exciting because it would mean dark matter is not an exotic particle, but something we already understand in principle, just formed in the early universe under extreme conditions. Detecting or ruling out primordial black holes would be a major step in solving the dark matter mystery. Current observations constrain but don't rule out certain mass ranges, so the possibility remains open. Fact 162. Black holes challenge our concepts of identity and continuity. If a person falls into a black hole, from an outside perspective, they never fully cross the horizon but are frozen and fade from view. From their own perspective, they cross smoothly and hit the singularity. In what sense does the person still exist after crossing the horizon if they're causally disconnected from the outside universe? These questions touch on philosophy of mind, identity, and existence. Fact 163. The amount of energy extractable from a black hole through the Penrose process or Blandford-Zenajec mechanism is enormous. A single supermassive black hole could power an entire civilization for billions of years if we could harness it. This has led to speculation about Kardashev Type 2 or Type 3 civilizations, advanced civilizations that harness energy on stellar or galactic scales, possibly using black holes. There's no evidence such civilizations exist, but if they do, black holes would be prime energy sources. Fact 164. The unpredictability of quantum mechanics meets the determinism of general relativity at black holes, creating deep tensions. Quantum mechanics says the future is probabilistic, given only in terms of probabilities. General relativity says the future is determined by initial conditions and the field equations. At the event horizon and singularity, these worldviews collide. Resolving this tension is part of the quest for quantum gravity. Fact 165. Black holes might preserve information holographically on the event horizon, with the three-dimensional interior encoded on the two-dimensional surface. This holographic encoding, if true, would mean that the interior of the black hole is not really a separate region, but is a different description of the same information on the horizon. This idea, inspired by the holographic principle, suggests that space itself might be emergent, not fundamental, arising from quantum information on boundaries. Fact 166. The maximum efficiency of energy extraction from a black hole is about 42% for a maximally spinning black hole through accretion processes. This exceeds any other known natural energy source. In comparison, stars convert less than 1% of mass to energy. This efficiency makes accreting black holes the most luminous steady-state objects in the universe. Fact 167. Every black hole has a unique signature in its gravitational wave emission depending on its mass and spin. By detecting gravitational waves from many black holes, we can build a population model, understanding the distribution of masses and spins, which tells us about how black holes form and evolve. This is analogous to studying a population of animals to understand their ecology. Gravitational wave astronomy is giving us black hole demographics. Fact 168. The confirmation that black holes exist and behave as general relativity predicts is one of the greatest triumphs of theoretical physics. Einstein published General Relativity 1915. Black hole solutions were found shortly after, but confirming they exist took a century. This shows the power of theory to predict nature and the importance of observations to confirm theory. It's a beautiful example of how science works when it works well. Fact 169. Black holes, despite being the darkest objects in the universe, have illuminated our understanding of reality more than almost anything else. They've taught us about space-time, gravity, quantum mechanics, thermodynamics, information, and the limits of knowledge. They've pushed technology and observation to new frontiers. They've inspired wonder and curiosity across generations, and they still hold mysteries we haven't solved. The journey to understand black holes is far from over, and the discoveries yet to come will undoubtedly be as surprising and profound as those we've already made. And there you have it, 169 facts about black holes, from the basics of what they are to the cutting edge of theoretical physics and cosmology. We've journeyed from event horizons to singularities, from Hawking radiation to gravitational waves, from stellar mass black holes to the supermassive monsters at the centers of galaxies. We've explored their past, their present, and their role in the universe's future. Black holes are the most extreme, most fascinating, most mysterious objects in the cosmos. They're laboratories for testing our deepest theories, windows into quantum gravity, and keys to understanding the nature of reality itself. If you've made it this far, thank you. Thank you for spending this time with me exploring the darkness at the heart of the universe. If this journey has left you in awe of black holes, if you're seeing the cosmos differently now, if you have a new appreciation for the invisible monsters lurking in space, then please hit that like button and subscribe to Sleepy Copernicus. Leave a comment telling me which fact surprised you the most, which one you want to learn more about, or if there's a topic you'd like me to explore next. The universe is vast, mysterious, and full of wonders. Black holes are just one part of that cosmic story, but what a part they are. Until next time, keep looking up, keep asking questions, keep exploring, and remember that somewhere out there in the darkness between the stars, black holes are spinning silently, waiting to teach us more secrets about the universe we call home. Clear skies, and see you in the next video.